Have you ever wondered if there's another world, far beyond the reach of our solar system, that might be harboring life? A planet not in some distant science fiction universe, but circling a nearby star, cloaked in mystery and wonder, whispering possibilities through the vastness of space. The story of Gliese 581c is a tale that brought that dream closer than ever before. When it was discovered, the world stood still for a moment. Newspapers printed headlines with exclamations like "Second Earth Found" and "Habitable Planet Discovered." For scientists, dreamers, and skeptics alike, Gliese 581c was more than a rocky planet 20 light-years away. It was a spark, a signal, a promise that the Earth might not be unique in its ability to cradle life. Gliese 581c orbits the red dwarf, star Gliese 581, situated within the constellation Libra. Discovered in April 2007 by a team of astronomers led by Stefan Udry at the La Silla Observatory in Chile, this planet marked a monumental leap forward in the search for exoplanets, particularly those that might be able to support life. The planet is the third one from its star in the Gliese 581 system, and it was one of the first rocky exoplanets found in what was initially thought to be the star's habitable zone. The mere possibility of its habitability ignited a frenzy across scientific and public communities alike. For a moment, humanity dared to believe that Gliese 581c could be the second Earth. But as we began to learn more, that dream became increasingly complex, murky, and scientifically contentious. To understand why Gliese 581c was so exciting, we must first understand the environment it resides in. The star Gliese 581 is a red dwarf, smaller and cooler than our Sun, emitting a faint red glow rather than the bright white-yellow blaze of our own star. Red dwarfs like Gliese 581 are by far the most common type of star in the Milky Way galaxy, making up about 75% of all stars. They burn slowly, have extraordinarily long lifespans, and are highly stable over long periods. An essential trait when considering the long evolutionary timeline needed for complex life to emerge. However, their small size and cool temperature also mean that the habitable zones around them are much closer in. Planets must orbit extremely close to the star in order to be warm enough to have liquid water, and this proximity introduces challenges of its own. Gliese 581c is about 1.5 times the size of Earth, and at least 5 times as massive. It completes an orbit around its host star in just about 13 Earth days, a number that reflects how tightly it hugs its dim sun. In this tight orbit, the gravitational pull is immense, and such planets are likely tidally locked, meaning one side of the planet perpetually faces the star, basking in endless daylight, while the other side remains in eternal darkness. This has profound implications for the climate and potential habitability of the planet. The day side could be scorching hot, while the night side might be frigid and frozen. Yet perhaps in the twilight zone, the narrow band between the two extremes, a balance could exist where temperatures are just right for liquid water and perhaps life. Initial estimations placed Gliese 581c firmly within the habitable zone, the sweet spot where liquid water could theoretically exist. This announcement was met with worldwide media attention, as it was the closest thing to an Earth twin we had found up to that point. Scientists began theorizing about its atmosphere, its potential oceans, its surface pressure, and whether clouds could swirl in its skies. Was it a paradise of warm breezes and shallow seas, or a hellscape of fire and ice? At the time, no one knew for sure, and so speculation surged forward. The mass of Gliese 581c indicates that it's likely a rocky planet, though we've never directly imaged it. We infer its existence and characteristics through radial velocity methods, measuring the slight wobble in its star caused by the planet's gravitational pull. While this method provides vital information about mass and orbital distance, it doesn't offer visuals, atmospheric data, or surface composition. Still, the tantalizing parameters of Gliese 581c inspired new models, simulations, and studies. Yet, the more scientists investigated, the more they realized how little we truly knew. and how dangerous it was to assume Earth-likeness from a handful of parameters. The initial claim that Gliese 581c was in the habitable zone was later called into question. More detailed models of the star's luminosity and temperature suggested that the planet might actually lie just inside the inner edge of the habitable zone, too close to the star. That would make the planet more similar to Venus than Earth, potentially locked in a runaway greenhouse effect, with blistering surface temperatures and a thick, toxic atmosphere. The discovery that Gliese 581c may be more Venus-like than Earth-like dampened some of the enthusiasm, but also sparked new lines of inquiry. Could the planet have a thick cloud layer that reflects incoming radiation, helping stabilize its temperature? Might tidal locking not be as absolute as assumed, allowing for some thermal distribution across the planet? Could life still thrive underground or in protected microenvironments within the Terminator zone? These were not idle questions. They represented the birth of an entire new approach to habitability, one that didn't assume Earth was the perfect template, but rather explored the myriad ways life might adapt to alien environments. Even more fascinating was the debate around Gliese 581c's position in a larger family of planets in its star system. Over the years, astronomers identified several additional planets orbiting Gliese 581. Gliese 581b, 581d, and 581e were discovered before or around the same time. Then, potential discoveries of Gliese 581f and 581g were announced, but those were met with skepticism and later retracted or disputed due to questions over the data. Particularly, Gliese 581g was a highly anticipated find, a planet potentially even more hospitable than 581c, but controversy over whether it actually exists remains unresolved. Amid this confusion, Gliese 581c retained its notoriety, not necessarily as the most habitable exoplanet, but as the first one that made us believe it might be possible. Its discovery was a turning point in planetary science. Before Gliese 581c, the majority of known exoplanets were gas giants, massive, Jupiter-like worlds with no solid surface. Gliese 581c was one of the first small, rocky exoplanets in a star's habitable zone to be identified, representing a monumental leap forward in our ability to detect Earth-like worlds. It demonstrated that our methods were improving, that our reach was expanding, and that we were beginning to probe the galaxy not just for planets, but for homes. The scientific tools used to analyze planets like Gliese 581c were themselves evolving. Spectroscopy, transit observations, and computer simulations began offering ways to understand exoplanet atmospheres, weather patterns, and orbital dynamics. While we still lack a telescope capable of directly imaging Gliese 581c or sampling its atmosphere, each new generation of instruments brings us closer. The James Webb Space Telescope, launched in 2021, began probing atmospheres of distant exoplanets, and although Gliese 581c is too faint and close to its star for direct atmospheric analysis today, future instruments could change that. What's even more intriguing is how Gliese 581c fits into humanity's growing awareness that the universe may be teeming with planets. Since its discovery, thousands of other exoplanets have been found. Some are hot Jupiters skimming the surfaces of their stars. Others are ice giants floating far from the warmth of their suns. But among them, a rare few sit in that precarious, golden habitable zone. And Gliese 581c was the first one that truly made headlines. It marked the moment when other Earths shifted from fantasy into something resembling science. The psychological impact of Gliese 581c cannot be overstated. For the public, it was a revelation. For scientists, it was a call to arms. And for philosophers and ethicists, it posed tantalizing questions. If we found life there, what would it mean? For identity? For the idea that we are alone? Could we ever go there? Should we send probes? Messages? Could our descendants one day stand upon its surface and look back toward Earth as a distant point of light? But those visions were tempered with realism. The proximity to its star likely subjects Gliese 581c to intense stellar flares and radiation, common with red dwarfs. If the planet lacks a magnetic field, its atmosphere could be stripped away over time. Or perhaps its thick atmosphere protects it, creating a kind of alien shield under which exotic life might thrive. The truth remains hidden for now, but that hasn't stopped us from dreaming. The questions surrounding Gliese 581c's atmosphere have remained central to its potential as a habitable world. Though we lack direct measurements, scientists have speculated about a range of possibilities based on models of planetary formation and atmospheric retention. Given its mass, significantly higher than Earth's, Gliese 581c may possess a stronger gravitational pull, which could allow it to hold on to a dense atmosphere for billions of years. But what would that atmosphere be made of? If it resembles Venus, it could be dominated by carbon dioxide, resulting in high surface pressures and temperatures that would render the surface utterly inhospitable to life as we know it. However, if some mechanism, such as cloud albedo or a reflective haze, keeps surface temperatures moderated, even a thick CO2 atmosphere might allow for habitable conditions in certain regions. Moreover, scientists have explored whether Gliese 581c could harbor a significant amount of water. Water, of course, is considered one of the essential ingredients for life. The planet's density suggests it is likely rocky, but some models leave open the possibility that it could be an ocean planet with deep global seas, depending on its formation history. If the planet formed in a region rich in volatiles and retained a thick envelope of water, it might be covered in hundreds of kilometers of ocean with pressures and conditions unlike anything found on Earth. These high-pressure environments could give rise to unfamiliar chemical and physical phenomena, like high-pressure ice phases or supercritical water layers, creating a deeply alien ocean ecology, if life could adapt to such extremes. The nature of Gliese 581c's potential magnetic field also contributes to the conversation. Earth's magnetic field serves as a shield, protecting us from harmful solar radiation and preserving our atmosphere. A tidally locked planet like Gliese 581c may have slower core dynamics, potentially reducing the chance of a strong magnetosphere. This would leave the planet vulnerable to stellar wind stripping, especially given how active red dwarfs can be. However, certain models suggest that if the planet's core is still active and molten, and if convection is occurring within it, a magnetic field could still be sustained. And even in the absence of a global magnetic field, localized magnetic anomalies or dense atmospheric shielding might still allow surface or subsurface life to endure. One of the most captivating possibilities lies in the Terminator zone, the ring-shaped region between the planet's day side and night side. If Gliese 581c is tidally locked, this band might feature relatively stable temperatures, moderate light levels, and minimal radiation extremes compared to either the scorching day side or the frozen night side. In science fiction and even some scientific models, this region is often imagined as the most likely place for life to survive. Picture a land of eternal twilight, where the sun never rises or sets, but hovers eternally at the horizon. Winds might flow from the hot side to the cold side, creating dynamic weather systems and possible cloud formations. Such a region could support microbial life, or even more complex organisms if the environmental conditions are right. But perhaps even more enticing is the idea of life evolving not on the surface, but beneath it. Subsurface life, hidden in underground oceans or shielded cavern systems, could be insulated from the harsh conditions of space and stellar radiation. On Earth, extremophiles thrive in deep-sea hydrothermal vents, acidic caves, and underground aquifers, environments once thought entirely lifeless. If Gliese 581c has geothermal activity or a subsurface ocean heated by tidal forces, life could have found a refuge deep beneath its crust. The possibility of complex underground ecologies adapted to darkness, pressure, and chemical energy sources cannot be ruled out. The broader implications of Gliese 581c go beyond biology and touch on the evolution of planetary systems. The Gliese 581 system as a whole has become a rich case study in planetary architecture. With multiple planets of various sizes and masses orbiting a single red dwarf, the system offers insights into how solar systems form and stabilize. Orbital resonances, gravitational interactions, and migration histories all paint a picture of dynamic evolution, with planets potentially moving inwards or outwards over time, altering their climates and habitability. These interactions could influence everything from volcanic activity to atmospheric loss, creating an ever-changing environment on Gliese 581c. One major challenge in studying Gliese 581c is the limitations of our technology. Because it doesn't transit its star from our perspective on Earth, we can't use the transit method to analyze its atmosphere, as we can with other exoplanets. That leaves us reliant on indirect methods and theoretical modeling, which means every new piece of data can change our understanding dramatically. For example, small shifts in estimates of the star's luminosity or the planet's orbit can determine whether Gliese 581c is too hot, just right, or too cold for liquid water. These uncertainties don't undermine its importance. They underscore just how complex and delicate the search for another Earth truly is. The debate around Gliese 581c's habitability also highlights the evolving definition of the habitable zone. For decades, scientists used a simplified model focused on surface temperature and the potential for liquid water. But Gliese 581c forced us to re-examine that approach. We now know that factors like atmospheric composition, planetary tilt, orbital eccentricity, geological activity, and stellar radiation must all be considered. What initially seemed like a straightforward discovery, the first potentially habitable exoplanet, quickly became a deeply nuanced case study. This complexity has made Gliese 581c one of the most studied and discussed exoplanets in history, even as newer, potentially more habitable worlds have been discovered since. Despite the controversies and limitations, the cultural impact of Gliese 581c is undeniable. It was featured in documentaries, science fiction books, and countless news stories. It brought the idea of alien worlds into living rooms around the globe. For many people, it was the first time they heard of the term exoplanet or learned that other solar systems even existed. In this way, Gliese 581c served as an ambassador of sorts, not necessarily of life itself, but the cosmic possibilities that await us. It was a reminder that we are part of a much larger galactic neighborhood, and that our curiosity can reach across light years. This curiosity even extended to active attempts at contact. In 2008, a message containing text, images, and audio from people around the world was beamed to the Gliese 581 system via the RT-70 radar telescope in Ukraine. Dubbed a message from Earth, this symbolic transmission was a modern echo of humanity's eternal question: are we alone? It will take about 20 years to reach its destination, and if anyone or anything were to reply, it would be another 20 years before we received an answer. The odds of success are infinitesimally small, but the act itself is what mattered. Gliese 581c had, for a moment, become a bridge between worlds, real or imagined. While newer exoplanets, such as Kepler 186f, Proxima Centauri b, and TOI 700d have since entered the spotlight as potential Earth analogs, Gliese 581c remains a pioneer. It marked the first time humanity seriously contemplated the real possibility of life beyond our solar system in a scientific context. Its legacy continues in the countless research papers, grant proposals, and educational materials that followed. And as telescope technology advances, we may one day revisit Gliese 581c with more powerful instruments, capable of peering into its atmosphere, measuring its surface reflectivity, or even capturing the first direct image of its alien terrain. The emotional gravity of Gliese 581c lies in its timing. It appeared when the search for exoplanets was in its relative infancy, and it gave the world a sense of direction. Like a lighthouse in the dark, it showed that other worlds could be within reach, not in terms of travel, perhaps, but in terms of understanding. And understanding, after all, is the first step toward connection. We may never walk its surface. We may never hear signals from its depths. But Gliese 581c changed us. It widened our view of what might be possible. It awakened a longing that continues to fuel the engines of discovery. And so we continue watching, listening, calculating. With every new telescope and every new model, Gliese 581c remains a part of the conversation. It's a reminder that discovery is not a destination. It's a journey. A long, winding journey filled with hope, disappointment, wonder, and revelation. In the vast tapestry of the cosmos, Gliese 581c is just one thread. But it is a thread that shimmers with promise, pulling our gaze upward, outward, forward. The mystery of Gliese 581c isn't just one of raw data. It's a philosophical challenge, a mirror that reflects our own assumptions about life, habitability, and our place in the universe. When we look at Gliese 581c, we're not just studying a distant rock orbiting a faint red star. We are probing the fundamental conditions that make Earth special, or not. We are questioning whether biology, as we know it, is a universal inevitability or a cosmic accident. Gliese 581c sits at the intersection of what we know and what we dream, straddling the line between the familiar and the alien. As our technology continues to advance, the methods we use to observe exoplanets like Gliese 581c grow more sophisticated. Instruments such as the James Webb Space Telescope, while focused primarily on planets that transit their stars, provide critical insights into exoplanetary atmospheres and surface conditions. Meanwhile, ground-based observatories using adaptive optics and radial velocity refinements offer better constraints on mass, orbital eccentricity, and even potential exomoons. Though Gliese 581c doesn't transit its star, researchers continue to push observational techniques to indirectly characterize it. Spectral analysis of its star, Gliese 581, yields more refined data, enabling scientists to update models of the planet's potential climate and environment. One of the fascinating aspects of Gliese 581c's orbit is its proximity to the inner edge of the star's habitable zone. Being so close to the star, Gliese 581c receives a level of stellar radiation that may be excessive for habitability by Earth standards, unless specific moderating conditions exist. The nature of red dwarfs complicates this even further. Though they are relatively cool compared to the Sun, red dwarfs can be far more volatile. Flares and bursts of X-ray and ultraviolet radiation could periodically bombard the planet, eroding any protective atmosphere over time unless a very strong magnetic field or thick atmospheric layer counteracts it. These flares are known to be frequent in younger red dwarfs, though the Gliese 581 system is considered to be relatively old, possibly between 7 to 11 billion years. This old age may mean that Gliese 581c has experienced billions of years of atmospheric loss or geological transformation, significantly altering its early characteristics. But longevity also means potential. Life on Earth took over 1 billion years to emerge after the planet's formation. If Gliese 581c had any favorable window, no matter how brief, it could have given rise to microbial life. And if subsurface environments were stable enough, that life could have adapted, evolved, and persisted possibly to this day. The history of Gliese 581c, therefore, is not just written in its orbit or composition. It's a narrative of time, change, and resilience. It is a reminder that the conditions for life are not static, and even a world that seems inhospitable today might have been vibrant in the past. The concept of super-Earths plays a pivotal role here. Gliese 581c was one of the first widely publicized examples of this category, a planet more massive than Earth, but still likely terrestrial. Super-Earths are now considered potentially more habitable than Earth-sized worlds in some cases. Their greater mass allows for longer geological activity, more stable atmospheres, and stronger magnetic fields, each a protective factor for long-term life sustainability. If Gliese 581c possesses plate tectonics, for example, it could recycle carbon and stabilize its climate through a geochemical feedback loop, much like Earth does. However, a higher gravity environment could also pose challenges, such as inhibiting certain atmospheric processes or making it harder for complex land-based life to evolve due to increased biomechanical demands. In imagining life on Gliese 581c, we are invited to consider forms that are completely alien yet governed by universal principles. Life might not be carbon-based. It could operate using different solvents, energy cycles, and biochemistries. It might be chemotrophic, deriving energy from chemical reactions deep within the crust, or it could rely on geothermal gradients to sustain its metabolic processes. Alternatively, life could have existed and then gone extinct, leaving behind a dead but once living world, an alien Mars, so to speak. In that case, the planet might carry biosignatures or fossilized evidence buried beneath its surface, waiting for detection by future technologies. There's also the matter of what we project on as such distant worlds. Humans have a tendency to anthropomorphize planets, to imagine them as extensions of Earth, as blank canvases for colonization or salvation. Gliese 581c has often been framed as a second Earth in popular media, despite the many scientific uncertainties. This narrative speaks not only to our curiosity, but to our longing for survival, for expansion, for meaning. In envisioning other habitable worlds, we confront our own fragility. Earth's climate, atmosphere, and biosphere are astonishingly complex and delicate. The idea that we might find or create another Earth elsewhere, even if only in concept, fuels our pursuit of knowledge and exploration. Yet Gliese 581c also humbles us. It reminds us that planets are not interchangeable. Habitability is not a binary switch. It is a tapestry woven from dozens of variables: distance, atmosphere, rotation, stellar activity, magnetic shielding, and countless others. A planet may be habitable in one epoch and deadly in the next. It may appear friendly to telescopes, but hide a hostile environment. The deeper we look, the more we appreciate the uniqueness of Earth and the staggering complexity required for life to take root. Astrobiologists studying Gliese 581c often explore the broader implications for the frequency of life in the universe. The Drake equation, once a speculative framework, gains nuance with each exoplanet discovery. If Gliese 581c turns out to be lifeless despite appearing Earth-like in key metrics, it may suggest that habitability is rarer than we hope, or at least that life is harder to detect than we imagine. On the other hand, if planets like Gliese 581c are common and varied, each with unique permutations of habitability factors, the odds may still favor a universe teeming with diverse life forms, evolving under wildly different conditions. The public's fascination with Gliese 581c also shaped the trajectory of space policy and funding. Its discovery helped validate exoplanet research as a major field of study, encouraging the development of new missions and telescopes. It played a role in shifting public discourse from "are there planets around other stars?" to "how many are habitable?" That shift, subtle but profound, reframed humanity's place in the cosmos. We no longer had to ask whether Earth was special in having planets. Now we could ask whether it was special in harboring life, a more urgent, more philosophical question. To this day, Gliese 581c remains a benchmark in the annals of exoplanet research. It serves as a case study in scientific caution, media exaggeration, and theoretical evolution. Its story is one of initial excitement, tempered by sobering reality, and sustained by unyielding curiosity. It reminds us that scientific discovery is not a moment, it's a process. Each new insight about the planet, its star, or its environment adds another layer to a complex portrait that is still incomplete. And in that incompleteness lies the wonder, a cosmic cliffhanger that beckons us forward. If humanity ever masters the technology for interstellar travel, Gliese 581c would likely be high on the list of exploratory targets. At just over 20 light-years away, it's within the realm of near-future speculation. Though no current propulsion technology could get us there within a human lifetime, concepts like fusion drives, laser sails, and generation ships have kept the dream alive. Should such a journey ever be undertaken, the explorers who first set foot near Gliese 581c will carry with them not only instruments and data, but the weight of centuries of human wonder. They would not just be astronauts. They would be historians, pilgrims, dreamers, inheritors of the questions we've been asking since 2007 and long before. And even if we never reach Gliese 581c in person, our intellectual journey there continues. Every telescope pointed toward the red glow of Gliese 581 is an act of scientific faith. Every model run on a supercomputer, every paper published, every diagram drawn, it's all part of the same quest. To know, to connect, to understand, and maybe, one day, to find that we are not alone. The allure of Gliese 581c is not solely based on its physical attributes or astronomical classification. It's rooted in what it represents. A moment in time when humanity realized that the universe might be more populated than previously imagined. When it was announced in 2007, the world paused. Headlines worldwide shouted the news. People who had never cared about space suddenly looked up. Students asked their teachers about exoplanets. Scientists received a surge of funding interest. Writers, filmmakers, and artists all turned their imaginations toward this new world. Nestled in the constellation of Libra, orbiting an unassuming red dwarf 20 light-years away. That announcement was more than a scientific finding. It was a cultural event. It marked the beginning of a new phase in exoplanet science, where the term Earth-like began to carry both hope and controversy. Scientists began scrambling to better define what habitable really meant. Could a planet be in the habitable zone and still be utterly inhospitable? What if its atmosphere was made entirely of carbon dioxide or sulfuric acid? What if the planet had no magnetosphere and its surface was bombarded by radiation? What if it rotated so slowly that one side was scorched while the other froze? These were no longer philosophical questions. They were practical ones, urgent ones, driving new missions and hypotheses. Gliese 581c, because of its early fame, became a testbed for these questions. It revealed the limits of our knowledge and pushed scientists to develop more nuanced models. One of the most important of these models was the runaway greenhouse effect. This idea suggested that, like Venus, Gliese 581c could have been trapped in a state where its surface temperature spiraled upward due to thick atmospheric gases, creating a hellish world rather than a temperate one. This was particularly relevant because of the planet's location so close to the inner edge of the habitable zone. The possibility that it was just slightly too close to its star to support life sparked a cascade of reevaluations about other supposedly habitable exoplanets. Interestingly, this skepticism didn't diminish interest in Gliese 581c. It amplified it. Just as the mystery of Mars deepened after we learned it might once have had water, the intrigue surrounding Gliese 581c grew as new complexities emerged. This paradoxical relationship between uncertainty and curiosity became one of the central themes in exoplanet exploration. The less we know with certainty, the more driven we are to uncover the truth. And in the case of Gliese 581c, that truth remains tantalizingly out of reach. The planet's mass, about 5.5 times that of Earth, places it firmly in the super-Earth category. This means it likely has a solid surface and possibly a thick atmosphere, although the exact composition remains unknown. If the planet has a dense atmosphere, it might support surface temperatures that stabilize the climate, protecting it from the extremes of tidal locking. On Earth, atmospheric dynamics like jet streams and ocean currents regulate heat distribution. If Gliese 581c has similar processes, either through air or some form of fluid, it might maintain habitable conditions over certain regions, perhaps in a twilight band between day and night. This opens up an exciting possibility: partial habitability. Earth is globally habitable, but Gliese 581c might only support life in specific zones. That might sound limiting, but for scientists and astrobiologists, even a sliver of potentially stable surface is incredibly significant. It means there's a chance for life to evolve, survive, and adapt, even under extreme constraints. Organisms on Earth have thrived in environments that we once thought were uninhabitable. Hydrothermal vents, Antarctic ice sheets, acidic lakes, radioactive zones. If Gliese 581c has an equivalent, say a geothermal pocket, a protected valley, a subterranean aquifer, then life could find a foothold there. This theory fuels a broader movement in exoplanet science toward understanding niches of habitability. Rather than viewing planets as globally habitable or not, scientists now look for localized regions where life might exist. These microhabitats could be the key to detecting biosignatures, chemical indicators of life, in future observations. And if Gliese 581c has any kind of dynamic weather, seasonal variation, or geological activity, the chances for such niches increase. Over time, debates about the planet's orbital parameters also began to change. Initially believed to have a nearly circular orbit, later studies suggested the possibility of more eccentricity. This would mean that the planet experiences fluctuations in its distance from its star, leading to periods of relative warmth and cold. These seasonal effects, while more extreme than those on Earth, could still allow for windows of habitability, especially if buffered by a dense atmosphere or internal heat. And what of internal heat? One overlooked possibility is the role of tidal heating. If Gliese 581c is gravitationally interacting with other planets in its system, such as the once-confirmed Gliese 581d or the debated Gliese 581g, that might experience internal friction, warming its core. This same phenomenon keeps Jupiter's moon Io volcanically active and Europa's subsurface ocean in a liquid state. For Gliese 581c, tidal heating could create volcanic activity, hydrothermal systems, or even underground oceans, environments ripe for microbial life. This brings us to another profound idea, that life on Gliese 581c, if it exists, might not be surface-bound. Just as Europa and Enceladus may host life in subterranean oceans beneath icy shells, Gliese 581c might be a planet where life is hidden deep below, shielded from stellar flares and climate instability. This life wouldn't require sunlight. It would rely on chemical gradients, mineral interactions, and geothermal energy. It would be alien not just in form, but in fundamental lifestyle, surviving without a star, thriving without a sky. The growing body of research around these possibilities continues to expand our definition of what a habitable world can be. And Gliese 581c has inspired many such redefinitions. In exoplanet classification systems, planets used to be divided simply by size or distance from their star. Now, categories are more refined. We consider atmospheric pressure, stellar variability, magnetic protection, plate tectonics, axial tilt, and orbital resonance. These factors, when applied to Gliese 581c, turn it from a speculative candidate into a case study, one whose details are still being interpreted and reinterpreted with each new scientific advancement. And we haven't even touched the cultural impact in full. Gliese 581c is often used in science education to explain the search for life. It appears in documentaries, science fiction novels, podcasts, and lectures. It symbolizes the frontier, not just the final one, but the active one. It reminds us that space is not just something we look at, it's something we analyze, decode, and eventually touch. Artists have painted it, composers have written about it, and thinkers have used it as a metaphor for unknown potential. In that way, Gliese 581c isn't just a planet. It's an idea, a canvas for projection, a placeholder for all the hopes we assign to the stars. In considering the ethics of contact, colonization, or exploration, Gliese 581c is also a vital entry point. Suppose, just for a moment, that life already exists there. Would we have the right to interfere? Would our curiosity be justification enough to alter its pristine environment? These questions matter, not only for the distant future, but for the present philosophy of space exploration. Planetary protection is no longer limited to the solar system. Worlds like Gliese 581c force us to craft policies that span the galaxy, governing how we interact with ecosystems that may be entirely alien yet fundamentally precious. The future of studying Gliese 581c lies in continued observation, simulation, and maybe one day, exploration. Technologies like direct imaging, gravitational microlensing, and advanced spectrometry will refine what we know. Perhaps one day we will detect atmospheric components like methane, oxygen, or even chlorophyll-like reflectance. Perhaps we'll hear something, radio signals, electromagnetic anomalies, a whisper from a distant civilization. Or perhaps we will learn definitively that Gliese 581c is dead, barren, and lifeless. But even if we do, its value will not be diminished. Its discovery has already changed the world. It has already reshaped our collective imagination. It has already served its purpose as a milestone in the journey toward understanding our place in the cosmos. Gliese 581c is not just a rocky body orbiting a red dwarf. It is a chapter in our story, a long, unfolding, unfinished story that spans from the first spark of curiosity to the last light of a distant world. Even as Gliese 581c drifts silently around its parent star, it continues to exert a gravitational pull, not just on neighboring planets, but on human ambition, wonder, and our thirst for knowledge. Every telescope that gazes toward the Libra constellation, every simulation rendered by supercomputers, every paper published by astronomers, Gliese 581c is at the heart of it all, quietly shaping the future of exoplanetary science from across the void. The technological advancements driven by the study of Gliese 581c are, in themselves, staggering. When it was discovered, radial velocity was the primary method for detecting exoplanets. But over the years, astronomers realized the need for even more sensitive instruments to decipher whether Gliese 581c was habitable or not. The limitations of radial velocity, especially when measuring small planets around active red dwarfs, led to innovations in precision spectroscopy. Instruments like HARPS, High-Accuracy Radial Velocity Planet Searcher, had already proven their worth, but the quest for clearer insights into Gliese 581c inspired an entire generation of next-gen tools: Espresso, Carmines, and eventually space-based missions like TESS and Plato. These instruments didn't just help clarify the mystery of Gliese 581c. They revolutionized our ability to study hundreds, then thousands, of other exoplanets. In that sense, the planet served as both a target and a training ground. It's a planetary Rosetta Stone. Crack its code, and you begin to crack the code of planetary habitability as a whole. But progress hasn't always been linear. In fact, one of the most fascinating aspects of Gliese 581c's legacy is how often the narrative surrounding it has changed. There were times when scientists believed the planet could be temperate, with liquid water oceans and breathable air. Later models revised that optimism, warning of searing temperatures and suffocating greenhouse effects. For a brief time, Gliese 581g, a purported sibling planet in the same system, stole the spotlight as a better candidate for habitability, only for its existence to later be cast into doubt. Through it all, Gliese 581c remained mysterious, steadfast, and provocative. Every time our understanding of it was updated, it forced us to reflect on the assumptions underpinning our models. What biases influence how we define Earth-like? What role does stellar activity play in making or breaking habitability? How do we weigh the influence of a planet's mass, composition, and atmosphere against its orbital location? Gliese 581c made us ask these questions not in abstract terms, but in practical, observable ones. The atmosphere of Gliese 581c remains a topic of intense speculation. If it exists, what could it be made of? High-resolution spectroscopy, though not yet fully capable of resolving the planet's atmospheric components directly, offers tantalizing hints. Theoretical models propose several possibilities. A thin, nitrogen-based atmosphere could, in theory, stabilize the planet's temperature if coupled with moderate greenhouse gases like carbon dioxide or methane. But a thick, Venus-like atmosphere dominated by CO2 could instead render the surface uninhabitable, with pressures and temperatures capable of melting lead. Some scenarios even propose a mirror world of sorts, a planet with a runaway greenhouse effect on one side and frozen glaciers on the other, with a narrow ring of survivability along the Terminator line, where day meets night. In this slender region, if it exists, temperatures might be just right for liquid water, creating a narrow but potentially life-friendly band around the planet. Could this be where life huddles in defiance of extremes? This idea of a twilight zone ecosystem is not science fiction. It is based on models that simulate atmospheric circulation on tidally locked exoplanets. If the atmosphere is dense enough, it can transfer heat from the starlit side to the dark side, creating dynamic wind systems and potentially temperate climates in intermediate regions. This has led to some of the most exciting simulation work in exoplanet climatology, calculations, and 3D models that now drive space agency planning and inform the design of future missions. And what about magnetism? Gliese 581c orbits a red dwarf, a type of star known for its violent flaring and radiation bursts. Without a magnetic field, the planet's atmosphere would be vulnerable to erosion over time, especially so close to its host star. But we simply don't know whether Gliese 581c has a magnetic field. If it does, that could be a saving grace, shielding its surface and retaining any volatile compounds essential for life. If it doesn't, then habitability becomes far less likely. Still, even an atmosphereless or unprotected Gliese 581c could hold secrets beneath its crust. The idea of subsurface habitability, life thriving in pockets beneath a planet's surface, grows more credible with every new discovery in our solar system. Mars has underground lakes. Europa has a global ocean beneath its ice. Even Mercury, scorched as it is, might have ice deposits in permanently shadowed craters. Why wouldn't a super-Earth like Gliese 581c, larger and possibly more geologically active, have its own hidden reservoirs? To study such possibilities, scientists have turned to exogeology, the theoretical study of planetary geology beyond Earth. By modeling internal heat flow, tectonic stress, and crustal composition, researchers attempt to predict how Gliese 581c might behave geologically. Could it have plate tectonics? Volcanism? If so, it might even recycle carbon, stabilizing its climate over long timescales. Such processes are critical on Earth. Without plate tectonics, our own climate would have collapsed long ago. All of this adds up to one reality. Gliese 581c is an extremely complex and dynamic system, even if its surface turns out to be sterile. It teaches us that the line between life and lifelessness is razor-thin and dependent on countless interconnected factors. Every data point we gather about it expands our knowledge exponentially, not just about this one planet, but about thousands of others across the cosmos. Culturally, the planet has also endured as a fixture in discussions about the Fermi paradox and the Drake equation. If Gliese 581c is habitable, or once was, then where is the evidence of intelligent life? Some thinkers have speculated that planets like Gliese 581c are common, and that life may be common as well, but intelligence might be rare or short-lived. Others argue that we simply haven't looked hard enough. Gliese 581c thus becomes more than a planet. It becomes a symbol of silence, of anticipation, and of the unknown. It's also a testing ground for our ethical and philosophical frameworks. What happens if we do find life there? Microbial, plant-like, or even intelligent? Would we still consider it a candidate for colonization? Would we extend rights to non-human life? These are not idle musings. They are questions that future generations of scientists, ethicists, and leaders will have to confront. And they are made real, grounded, and pressing by the ongoing study of Gliese 581c. The planet is also central to the story of human persistence. Even with decades of uncertainty, conflicting data, and changing theories, we keep returning to it. Why? Because Gliese 581c was one of the first planets that made us dream realistically, not just about the idea of alien life, but about the idea of alien Earths. It was not abstract like the Goldilocks zone or fantastical like warp drive. It was real, measurable, reachable, at least in theory. And because of that, it occupies a place in our collective memory that no future discovery can ever fully replace. As of now, we do not have direct images of Gliese 581c. We do not know what its mountains, valleys, or skies look like, if it even has them. But that hasn't stopped artists from painting it, scientists from simulating it, and storytellers from describing it. It exists vividly in our minds because we need it to. We need Gliese 581c to be real and habitable and beautiful because it keeps our hopes alive. It keeps us looking outward. It gives meaning to the darkness between stars. That hunger for meaning, fueled in no small part by Gliese 581c, has created ripple effects across fields as diverse as astrobiology, space policy, artificial intelligence, education, and even theology. The mere presence of this exoplanet in our scientific consciousness has made us ask better questions, build better instruments, and dream bigger dreams. It has led to new models of planetary evolution, expanded the boundaries of what we consider habitable, and sparked collaboration across nations, cultures, and generations of thinkers. And all of this, triggered by a distant, in the sky, barely visible to our finest instruments. Gliese 581c, with its tantalizing proximity and rich scientific complexity, has also fundamentally reshaped our understanding of red dwarf stars, arguably the most important stellar population in our galaxy when it comes to habitability. Prior to the discovery of this planet and others like it, red dwarfs were often dismissed as too volatile to support life-bearing planets. Their frequent flares and long-lived magnetic storms were thought to strip atmospheres and sterilize surfaces. But the potential for planets like Gliese 581c to orbit within these stars' habitable zones for billions of years, longer than the lifespan of our Sun, has forced a serious reevaluation. Today, red dwarfs are seen not as hostile, but as promising. Their planets are now top priorities for missions like the James Webb Space Telescope, which aims to probe their atmospheres directly. If we discover biosignatures around such stars, methane, oxygen, or other chemical imbalances, it could forever change our assumptions about where life is most likely to emerge. And none of that would be happening if Gliese 581c hadn't ignited the conversation. The significance of Gliese 581c also lies in the sheer number of scientific papers it has inspired. The planet has appeared in thousands of citations and is often used as a benchmark in studies involving planetary habitability, tidal locking, surface temperature modeling, and atmospheric evolution. It is not only a subject of speculation, but a tool, a theoretical playground upon which new models are stress-tested and refined. In this way, Gliese 581c has become something like a textbook planet, an educational archetype for teaching the science of exoplanets to a new generation of astronomers. Then there's the imaginative frontier, the way Gliese 581c has been absorbed into the cultural fabric. It has appeared in science fiction novels, documentaries, podcasts, and even music. Poets have written about it. Graphic designers have envisioned its landscapes. Video game worlds have drawn inspiration from its imagined environments. Even without setting foot on its surface, Gliese 581c has become part of the human story, a celestial muse orbiting 20.4 light-years away. We've also seen how its discovery created a domino effect within the exoplanet community. Once Gliese 581c was identified, attention turned to other planets in the same system. Gliese 581b, a larger Neptune-like planet. Gliese 581d, an even more promising candidate for habitability for a time. And the controversial Gliese 581g, which sparked a scientific tug-of-war regarding its very existence. The debate over Gliese 581g, widely reported in scientific circles and mainstream media alike, echoed back to Gliese 581c as astronomers began re-evaluating every data point with fresh scrutiny. Was Gliese 581c a true super-Earth or a false signal? Was its mass calculated correctly? Were we over-interpreting the available data? These questions triggered the rise of more advanced noise-filtering algorithms in exoplanet data analysis. Stellar activity can mimic planetary signals, creating false positives. The Gliese 581 system, with its variability and flare behavior, became a testbed for fine-tuning these techniques. The planet's magnetic field, or lack thereof, also raised questions about stellar winds and how these phenomena might differ between red dwarf systems and solar analogs. The end result was a refined methodology that benefits every future discovery, from Proxima b to the TRAPPIST-1 planets. But perhaps the most profound contribution Gliese 581c has made is philosophical. It sits in that perfect liminal space, not close enough to explore, yet not so far as to be irrelevant. It teeters on the edge of our technological capability, like a mirage shimmering at the far edge of a desert. This liminality makes it a unique intellectual touchstone, a place where science, philosophy, and emotion converge. What if life once existed there and vanished? What if it still exists, but is inaccessible forever due to distance? What if intelligent life emerged and perished millions of years ago? These are questions not of data, but of introspection, questions that make us consider the fragility of our own civilization. Gliese 581c is not just a mirror for science. It is a mirror for us. And so, the human obsession with this distant world continues. Research grants still reference it. Student theses still cite it. Engineers and visionaries still mention it in TED Talks and scientific keynotes. It has become a shorthand, a cipher, for everything we're trying to understand about planets, stars, life, and ourselves. The allure is more than just academic. There is a deep emotional resonance to Gliese 581c. When people talk about it, there's a sparkle in their voices, a mix of hope and longing. It's the same tone you hear when people speak of Atlantis, of El Dorado, of distant lands unseen but fervently believed in. Gliese 581c, like those mythic places, may never be reached. But unlike them, it is real. It's there. And that simple truth fills the night sky with a kind of silent music. As telescopes grow stronger and artificial intelligence continues to refine the analysis of planetary data, we inch closer to discovering whether Gliese 581c is barren rock or biological miracle. If it is the latter, it will become the most important discovery in human history. If it is not, then it will remain a powerful symbol of science, of humility, and of the limits of human reach. But even if Gliese 581c is dead and dry, its story will not end. It will continue to teach us. It will continue to be reanalyzed with each new wave of technology. And as humanity's search for life extends to other stars, it will forever be remembered as one of the first planets to make us believe, not just that life might exist elsewhere, but that we might one day find it. And still, there's so much more to say about its orbital resonance, about the influence of its parent star, about the implications of its thermal evolution and surface geochemistry. As we dive deeper into the intricacies of Gliese 581c, the more we realize how little we know and how much there is still to discover. The intricacies of Gliese 581c's thermal evolution, for instance, unravel a tapestry of planetary physics that stretches the limits of our current understanding. Unlike Earth, which benefits from a relatively stable climate mediated by plate tectonics and a protective atmosphere. Gliese 581c's potential heat distribution mechanisms remain highly speculative. Being so close to its star, it is likely tidally locked, presenting the same face to Gliese 581 at all times. This leads to stark contrasts in temperature between the day side and the night side. The day side may be scorched by constant stellar radiation, while the night side could be perpetually frozen, bathed in eternal darkness. If an atmosphere exists, and that remains a deeply debated point, it could act as a thermal moderator, redistributing heat and potentially creating a narrow habitable band along the Terminator line, where conditions might be neither too hot nor too cold. This so-called eyeball Earth configuration, where one side of the planet resembles a blistering desert and the other an icy wasteland, with a ring of temperate climate in between, opens up exciting avenues for modeling climate dynamics on exoplanets. Climate simulations suggest that with the right atmospheric pressure and composition, perhaps rich in carbon dioxide or even water vapor, a tidally locked planet like Gliese 581c could maintain liquid water in the twilight zone. That zone might be the best hope for habitability, and it draws parallels to polar ecosystems on Earth, which thrive despite harsh conditions. However, the potential for such a zone depends entirely on the planet's atmosphere, its thickness, composition, and evolution over time. Could Gliese 581c have retained an atmosphere for billions of years? Or has its proximity to the parent star caused it to lose its volatile elements, stripped away by stellar winds and radiation? This question lies at the core of many debates. Some models suggest that a strong magnetic field might protect the atmosphere, as Earth's does. But whether Gliese 581c could generate a magnetic field through internal convection in a liquid metallic core, for example, remains purely hypothetical. Then there's the matter of planetary geology. Is Gliese 581c geologically active? Does it experience tectonics, volcanism, or internal heating via tidal flexing caused by gravitational interactions with its star or neighboring planets? Geological activity would be crucial not only for atmospheric replenishment, but also for creating a carbon silicate cycle, a process that regulates long-term climate on Earth. Without such a mechanism, even a once habitable world could become a frozen wasteland or a greenhouse inferno over geological timescales. Some theorists propose that Gliese 581c may exhibit volcanism triggered by internal heating or even radioactive decay within its core. If so, the presence of geothermal energy could foster subsurface habitability, even if the surface is hostile. On Earth, we see rich microbial life in deep-sea hydrothermal vents, thriving in complete darkness, relying not on sunlight, but on chemical energy. This concept of chemosynthesis-based ecosystems could be the key to finding life on exoplanets that lie outside traditional habitable zones or in hostile surface environments. Moreover, the mineralogical makeup of Gliese 581c's crust, though entirely unknown, could influence its atmospheric chemistry and habitability. Is it a silicate-based world like Earth? Could it have vast deserts of oxidized iron, or a surface rich in metallic compounds that interact differently with radiation? These questions, while speculative, feed into models that attempt to simulate what Gliese 581c might look like, from albedo, reflectivity, to surface temperature variance. Adding to this is the role of stellar variability. Red dwarfs like Gliese 581 are known for their magnetic activity and flaring behavior, especially in their early years. While Gliese 581 is considered a relatively quiet star for its class, long-term monitoring is necessary to determine whether it emits periodic flares capable of sterilizing nearby planets. Ultraviolet and X-ray radiation could erode atmospheres and pose challenges to the formation of complex organic molecules. At the same time, such radiation could also catalyze the formation of prebiotic chemistry in certain conditions, an ironic duality that mirrors the role of UV radiation on early Earth. If we turn our attention to potential biosignatures, the discussion becomes even more speculative but equally riveting. What would we look for in Gliese 581c's atmosphere to infer the presence of life? Oxygen, while abundant on Earth due to photosynthesis, is not necessarily a universal biomarker. Other gases, methane, nitrous oxide, or even complex organics, could suggest biological processes. The ratio of these gases, along with the presence of disequilibrium chemistry, where certain compounds shouldn't coexist naturally unless continually replenished, could serve as red flags for life. These are the chemical fingerprints that the next generation of space telescopes aims to detect. Imagine, then, the first spectral analysis of Gliese 581c's atmosphere. A beam of light, filtered through the planet's air during a transit across its star, could carry the faintest traces of methane or ozone. That data, parsed by algorithms and checked against control samples, could hint at alien biology. Even a false positive would revolutionize our detection methods. But if it were real, if the spectral lines lined up perfectly, it would be the greatest discovery in the history of science. Of course, the transit method only works if the planet passes directly in front of its star from our vantage point. To date, Gliese 581c has not been observed to transit, meaning we can't use this method directly. That has led to calls for alternative approaches, direct imaging, polarimetry, and even future interstellar probes capable of remote observation. Some dream of sending a nanosatellite or light sail probe, riding a laser beam to reach the system in mere decades. An idea once relegated to science fiction, now being seriously considered through initiatives like Breakthrough Starshot. Beyond its physical characteristics, Gliese 581c also raises deep questions about the emergence of intelligence. If life did form there, could it have evolved into sentient beings? How would tidal locking, atmospheric dynamics, and limited day-night cycles influence cognition and culture? Would intelligence evolve in the twilight strip or in isolated geothermal pockets? How would such life perceive time, navigate space, or develop technology? These are questions with no answers, yet, but the act of asking them refines our philosophical toolkit. They remind us that intelligence, consciousness, and civilization are not uniquely human phenomena. They might be shaped by entirely different evolutionary pressures on worlds as foreign to us as Gliese 581c. The search for life, therefore, becomes a search for ourselves, not just biologically, but intellectually. The study of Gliese 581c also forces us to think long-term. Humanity has only just begun its journey into the cosmos. We have visited the moon, sent probes to the edge of our solar system, and discovered over 5,000 exoplanets. But Gliese 581c looms like a cosmic goalpost, a place we might one day send explorers, even if it takes generations. It represents the ultimate challenge, to reach out across the interstellar abyss, to close the gap between imagination and reality. And so, the saga of Gliese 581c continues, not just as a distant rock orbiting a small red star, but as a catalyst for thought, debate, and dreaming. It has made us question the definition of a habitable planet. It has challenged our understanding of planetary systems. It has redefined what it means to be Earth-like. And in doing so, it has brought us closer to the stars, not just physically, but intellectually and emotionally. Even now, as new data emerges and fresh theories unfold, we circle back to Gliese 581c to verify, to compare, to wonder. It is not the only exoplanet that matters, but it was one of the first that truly captured our imagination. And sometimes, that's enough to change the world. The importance of Gliese 581c extends beyond its immediate scientific intrigue. It has become a symbol of our collective quest to understand the universe and our place within it. In classrooms, research papers, documentaries, and thought experiments, Gliese 581c often stands as the first exoplanet that made the concept of another Earth feel tangible. It sparked a shift in perspective, reminding us that our solar system, once thought to be unique, is likely just one example in a vast, intricate gallery of planetary systems. The cultural and psychological impact of Gliese 581c cannot be overstated. Before its discovery, the idea of finding another habitable world was relegated largely to fiction. Afterward, it became a scientific goal, an aspiration that galvanized researchers and institutions. Funding for astrobiology increased. Telescopes were retooled. Public interest surged. People looked up at the night sky and began to truly believe that one of those dim red stars might host a planet not unlike our own. Gliese 581c did not just change astronomy, it changed how we dream. And yet, dreams alone are not enough. We need data, evidence, refinement of our theories. Every step forward depends on technology. Newer, more sensitive instruments capable of teasing out the secrets buried in starlight. Instruments like the James Webb Space Telescope, JWST, which peers into the infrared to study exoplanet atmospheres, and upcoming projects like the Extremely Large Telescope, YELT, and LUVOIR, Large UV Optical Infrared Surveyor, are all designed with worlds like Gliese 581c in mind. These telescopes might one day detect biosignatures, gases in the atmosphere that indicate the presence of life. They might find seasonal variations in carbon dioxide or oxygen, or identify unusual patterns of heat distribution that suggest artificial structures or even planetary-scale engineering. These possibilities remain speculative, but they're no longer absurd. They are, for the first time in history, technically within reach. While we haven't yet seen a transit of Gliese 581c, we can analyze the spectrum of light that reflects off the system. Photometric and spectrographic data, even in the absence of a transit, can hint at atmospheric characteristics such as cloud cover, albedo variations, and even surface composition. Light curves may suggest rotational periods, reflective surfaces, or seasonal weather. Advances in polarimetry, the study of light polarization as it reflects off different surfaces, could one day distinguish between land, water, and ice on distant exoplanets. In the case of Gliese 581c, detecting a glint of reflected light from a surface ocean would be revolutionary. On Earth, specular reflection, where sunlight reflects off a calm body of water, produces a characteristic glint. If such a signature were seen from Gliese 581c, it could be interpreted as evidence of surface liquid, possibly water. But the star's proximity and the planet's closeness to it make such observations extraordinarily difficult. The contrast ratio, the difference in brightness between star and planet, is extreme, requiring unprecedented precision. This is where missions like HabEx, Habitable Exoplanet Observatory, and concepts like star shades come into play. A star shade, deployed tens of thousands of kilometers away from a space telescope, could block out the starlight and allow the telescope to see the much fainter light from orbiting planets. In such a scenario, Gliese 581c might finally be observed in detail, its secrets unlocked by shadows and starlight. But even if Gliese 581c proves to be uninhabitable, its legacy is secure. It has paved the way for the discovery of many more potentially habitable worlds. Kepler 186f, Proxima Centauri b, TRAPPIST 1d, e, and f, to name a few. These worlds orbit stars of various types, from quiet M dwarfs to G-type suns like our own. And yet, the emotional weight of Gliese 581c endures. It was a pioneer. Its discovery also forced a re-evaluation of what habitable means. Traditionally, habitability was defined solely in terms of distance from a star, the Goldilocks zone, where temperatures allow for liquid water. But Gliese 581c reminded us that this is a vast oversimplification. Habitability involves atmosphere, magnetic field, geological activity, axial tilt, rotation, planetary mass, stellar behavior, orbital eccentricity, and a dozen other factors. It is a mosaic, not a single number. Even psychological models of extraterrestrial intelligence have been influenced by Gliese 581c. Because of its possible tidal locking and unique day-night structure, theorists have imagined what kind of minds could evolve in such an environment? Would creatures live entirely in twilight, avoiding the radiation of the day side and the freeze of the night side? Would their societies be structured around migration, shielding, or subterranean habitats? How would perception evolve without a traditional day-night cycle? Would time be measured differently? Would their myths and philosophies revolve around the red sun, always fixed in one part of the sky? Such thought experiments are speculative, of course, but they shape the way we think about consciousness. They help us escape the anthropocentric cage that confines our imagination. They make us realize that intelligence, if it exists elsewhere, may not resemble us at all, neither in biology nor psychology. Another dimension worth exploring is the potential for Gliese 581c to act as a stepping stone. If humanity ever develops the capacity for interstellar travel, it might be one of the first destinations. Even if it is not habitable, it could serve as a scientific outpost, a refueling station, or even a base of operations for missions deeper into the galaxy. Learning how to survive on a world with hostile surface conditions but potential underground resources would be a valuable lesson for colonization. It might teach us how to extract energy from tidal heating, how to shield against radiation, or how to terraform in the most extreme environments. The journey to Gliese 581c would not be short. At 20.3 light-years away, even a craft traveling at 10% the speed of light, a velocity far beyond our current capabilities, would take over 200 years to arrive. But human history is long. So too is our ambition. It's conceivable that one day, robotic emissaries or even human crews might set foot or track appendage on its surface. The timeline for such missions may stretch centuries into the future, but the seeds have already been planted. The study of Gliese 581c, its environment, its potential, and its mysteries serves as both roadmap and motivation. It is a reminder of what we can discover with patience, perseverance, and curiosity. And curiosity is the driving force behind all of this. We are creatures born on a pale blue dot, orbiting a modest star in a minor arm of a spiral galaxy. But we are also beings who ask questions, who dream of distant suns and shadowed planets. Gliese 581c is more than just a collection of data points. It is a beacon, a whisper across space that says, there is more. Come and see. We must continue to observe, to question, to simulate, to hypothesize. We must build better instruments, forge international collaborations, and train new generations of scientists, engineers, and explorers. The story of Gliese 581c is still being written, and it is being written by all of us, page by page, pixel by pixel, photon by photon. Whether it harbors life or not, whether it proves habitable or hostile, whether it remains forever out of reach or becomes our future home, Gliese 581c has already achieved something extraordinary. It has made us look up and wonder. It's easy to underestimate how profound that act of wondering really is. Across time and cultures, humanity has always looked to the sky for answers, but rarely has it looked at a single point, a faint, red star 20 light-years away, and asked with such urgency, could someone be looking back? That question, evoked by Gliese 581c, marked a turning point. For the first time, we weren't just imagining other worlds through myth or poetry. We were identifying them with coordinates and measurable properties. Gliese 581c's orbit and mass alone tell a story of extremes. With a mass at least 5 times that of Earth, it likely falls into the category of a super-Earth, a term used to describe rocky planets larger than Earth but smaller than ice giants like Neptune. The presence of such a planet so close to its parent star, nestled near the habitable zone, invited intense speculation. Could a super-Earth maintain plate tectonics? Could it have a molten core generating a magnetic field? Could it trap an atmosphere dense enough to retain heat, but thin enough to allow water vapor? Its proximity to Gliese 581, an M-dwarf star, also complicated our understanding. Red dwarfs are notoriously active. They exhibit strong stellar flares, magnetic storms, and spikes in radiation that could strip away atmospheres over time. Any planet within the habitable zone would need to be incredibly well shielded or possess regeneration mechanisms to survive this barrage. This is why understanding atmospheric retention on such planets became a priority in exoplanet research. Could a thick carbon dioxide envelope protect surface water from freezing despite a dim star? Could a strong magnetic field hold back the solar wind? Could a greenhouse effect balance the reduced stellar input? Simulations of Gliese 581c helped refine these questions and inspired hundreds of follow-up studies. It's ironic, perhaps, that what initially seemed like a perfect candidate for Earth 2.0 quickly became a poster child for the complexity of planetary habitability. The closer scientists looked, the less certain they were of its suitability for life. And yet, the ambiguity didn't kill interest. It amplified it. The very idea that we didn't know made the planet even more alluring. Gliese 581c then became a puzzle piece, a node in a web of inquiry that connects astrophysics, atmospheric chemistry, planetary geology, and even biology. This web is what makes exoplanet research so exciting. It's not just about finding planets. It's about finding patterns, rules, boundaries, and exceptions to those rules. It's about building a framework for understanding what makes a world alive or barren, volatile or stable. Even the process of disqualifying Gliese 581c as Earth-like was illuminating. It showed that habitability isn't just a matter of distance. It's a dance between star and planet, atmosphere and surface, heat and radiation. Every parameter matters. Orbital eccentricity, for instance, affects seasonal extremes. Axial tilt can determine whether a planet has seasons at all. Albedo influences how much light is absorbed or reflected. Each layer of complexity adds depth to our models. And as our models became more sophisticated, so too did our technologies. Gliese 581c's legacy isn't confined to theory. It has directly influenced telescope design, target selection, and instrument sensitivity. The Kepler Space Telescope, launched in 2009, focused on identifying Earth-sized planets in the habitable zones of other stars. While Gliese 581c wasn't in Kepler's field of view, it set the stage. It proved that such discoveries were possible. But they weren't science fiction anymore, they were science. The Transiting Exoplanet Survey Satellite, TESS, followed in Kepler's footsteps, scanning the entire sky for nearby worlds. Its mission was inspired by the promise of early discoveries like Gliese 581c. And as we venture further with JWST and future missions like the Roman Space Telescope, we continue to refine our methods, searching for biosignatures, atmospheric compounds, and the subtle hints that might indicate life. The potential discovery of life elsewhere, be it microbial, plant-like, or even intelligent, would revolutionize our understanding of biology and evolution. And Gliese 581c, regardless of whether it harbors life or not, is part of that revolution. It's part of a narrative arc of discovery, one of the first dominoes to fall in a chain reaction that's still unfolding. But let's zoom back in, imagine for a moment what it would feel like to stand on Gliese 581c, assuming survival is possible. The sky would be dominated by the dim red glow of its parent star, casting a perpetual ruby hue over the landscape. If the planet is tidally locked, that sun would hang unmoving in the sky, fixed in place like a cosmic lighthouse. The side facing the star would likely be scorched and dry, while the night side would be frozen and dark. But between them, a narrow ring of twilight circling the globe, conditions might be just right. That band of eternal dusk could be a haven, a zone of moderation. Perhaps winds would constantly rush from hot to cold, creating fierce and permanent weather systems. The terrain might be carved by wind and time into bizarre shapes. If life exists, it would be adapted to extreme gradients in light, temperature, and pressure. Organisms might harness energy in unfamiliar ways, perhaps through chemosynthesis or by absorbing infrared light. They would be alien not only in form, but in function. Or maybe Gliese 581c is completely dead, a silent world of rock and dust, devoid of atmosphere, its surface marked only by impact craters and tectonic scars. Maybe its moment came and went billions of years ago, if it ever came at all. Even that outcome teaches us something. A dead world still holds value. It teaches us what not to expect, what paths evolution might take, or fail to take. In this sense, every exoplanet is an experiment conducted by nature, a data point in a universe-wide biology lab. Gliese 581c is one of our first samples, and its mystery makes it even more precious. The mystery is compounded by human imagination. Gliese 581c has inspired science fiction novels, films, and art. It has been portrayed as a new home for humanity, a refuge from a dying Earth, a cradle for alien civilizations. These fictional depictions, while speculative, keep the public engaged. They transform cold data into stories, into vision, into curiosity. And that curiosity drives progress. It motivates young scientists. It attracts investment. It shapes educational curricula. It builds momentum for future missions. In this way, Gliese 581c is not just a planet. It is a symbol, a rallying point, a beacon of cosmic possibility. We may never set foot there, but the questions it raised will echo for generations. The questions Gliese 581c raised were not simply about its own environment, but about the entire tapestry of potential life-bearing planets across the cosmos. If one rocky, Earth-sized world can orbit a red dwarf star within a region near the habitable zone, how many more like it must be hidden in the folds of the galaxy? It wasn't long after the initial excitement surrounding Gliese 581c that the exoplanet community began to think in terms of statistics rather than isolated wonders. Scientists didn't just want to know if Gliese 581c was habitable. They want to know how common such planets were. This led to a concept that has become central in exoplanet research: the eta Earth, eta circle plus value. Eta Earth represents the fraction of stars that host at least one Earth-sized planet within their habitable zones. The discovery of Gliese 581c, despite its eventual demotion as truly habitable, gave scientists a vital early clue. If this planet existed around one of the nearest stars to our Sun, might that not suggest that small, potentially habitable planets are abundant? This statistical line of thinking galvanized NASA and other international space agencies to scale up their efforts. Kepler and TESS were direct products of this renewed sense of urgency, and each would go on to uncover thousands of exoplanets, many even more promising than Gliese 581c in terms of surface conditions and atmospheric prospects. Yet even with those future treasures, Gliese 581c remained a cornerstone of the narrative, like a fossil that proves a long-suspected evolutionary link. And that's part of what makes Gliese 581c such a phenomenon. Even in its imperfections, even in the likelihood that its conditions are too extreme for Earth-like life, it retains a kind of historical significance. It was an early symbol of possibility. It brought the idea of other Earths into public consciousness. News outlets around the globe ran headlines declaring the possibility of alien life. For the first time, non-specialists began to ask questions not about if exoplanets existed, but about what kind existed. This shift in public perception was more than symbolic. It influenced funding, collaboration, and even the curricula taught in universities. Astronomy departments saw an increase in students fascinated by astrobiology, planetary geology, and interstellar exploration. Fiction writers drew inspiration from the twilight band of Gliese 581c. Filmmakers began referencing in scripts. The planet became a muse not just for scientists, but for storytellers. From a scientific standpoint, Gliese 581c also forced a re-evaluation of what it means to be in the Goldilocks zone, a term often used to refer to the habitable zone around a star where temperatures are just right for liquid water. At first glance, Gliese 581c appeared to fit that description. But further modeling showed how deceptive that term can be. A planet's habitability is not just about where it sits in orbit. It's about atmospheric composition, rotation, tidal locking, magnetic shielding, cloud cover, and many other interrelated variables. Take, for instance, the issue of tidal locking. A planet that orbits so close to its star, as Gliese 581c does, is likely to become tidally locked, meaning one side always faces the star while the other is in perpetual darkness. This results in extreme temperature contrasts, a blistering hot day side and a frozen night side. For life to exist under such conditions, a planet would need strong atmospheric or oceanic currents to redistribute heat. On Earth, the oceans and atmosphere play a vital role in maintaining global climate balance. But what happens if the atmosphere is too thin or the planet lacks surface water? To make matters more complex, Gliese 581c orbits a red dwarf, or M-dwarf, star, a class of stars that, while long-lived and stable over billions of years, are known for their violent youth. Young M-dwarfs emit powerful flares and extreme ultraviolet radiation, often hundreds of times more intense than what the Earth experiences. This radiation could easily strip a planet of its atmosphere if that atmosphere is not replenished or shielded. Earth is protected by a magnetic field generated by the movement of molten iron in its core. But whether Gliese 581c has a similar internal dynamo is unknown and remains a critical question in determining its ability to support life. Yet even in uncertainty, Gliese 581c remains instructive. It taught astronomers that the habitable zone is not a promise, only a potential. It challenged them to refine their climate models, to include variables like stellar activity, atmospheric erosion, and geological feedback loops. As a result, the field of comparative planetology began to flourish. Scientists started to compare different exoplanets systematically, identifying patterns and outliers, and using these insights to improve our understanding of habitability across the galaxy. The lessons from Gliese 581c also had implications for the Drake equation, the famous formula proposed by Frank Drake in 1961 to estimate the number of intelligent civilizations in the galaxy. Each discovery of an Earth-like planet like Gliese 581c added weight to the variables in the equation, especially the fraction of stars with planetary systems and the number of planets per system that could potentially support life. Even if Gliese 581c turned out to be lifeless, its mere existence in our cosmic backyard tilted the odds in favor of life elsewhere. But let's revisit the more poetic side of Gliese 581c. One of the most compelling ideas to emerge from this discovery was the notion of a Terminator world. On a tidally locked planet, the boundary between the day and night sides, the Terminator line, could offer a narrow band of stability. It's here that temperatures might be moderate enough to allow liquid water. The idea captivated not just scientists, but philosophers and dreamers alike. What would life look like in the twilight zone of a distant planet? How would it evolve? How would it see the world? These questions are not just rhetorical. They inform the way we design future telescopes. They help determine what biomarkers to look for, like methane, oxygen, or water vapor, and how to interpret them. They guide us in identifying planets where conditions might be right not just for life as we know it, but for life as we don't yet understand. Gliese 581c has also been central to conversations about interstellar communication. When it was first discovered, some proposed that it might be a good target for active SETI, the idea of sending intentional signals to potentially habitable worlds. In 2008, a project called A Message from Earth sent a radio signal toward the Gliese 581 system using Ukraine's RT-70 radar telescope. The signal, traveling at the speed of light, is expected to reach Gliese 581c in 2029. If any intelligent beings reside there, and if they're listening, they could choose to respond. That response would reach Earth no sooner than 2049. Whether or not such a reply ever comes, the symbolic act of reaching out to another star system was profound. It marked a shift from passive observation to active engagement. It turned Gliese 581c from a data point into a conversation partner, even if that conversation is one-sided for now. It also raised ethical questions. Should we be advertising our presence to unknown civilizations? What if the consequences are dire? These debates continue to this day, and Gliese 581c is often cited in the arguments. Then there's the question of colonization. Even if we someday develop the technology to reach nearby star systems, would Gliese 581c be a viable target? At 20.4 light-years away, it's relatively close in cosmic terms, but still unfathomably distant with current propulsion technologies. A probe traveling at 10% the speed of light would take over 200 years to get there. And assuming we could send humans, the environment would be harsh, the gravity significantly higher than Earth's, and the day-night cycle non-existent. Terraforming such a world would be a task beyond even our most ambitious science fiction dreams. Yet still we dream. Gliese 581c remains a fixture in the collective imagination of our species. Not because it's perfect, but because it was first. It was the first world that truly made us wonder, not in abstract terms, but with tangible data, if we are alone. That wonder has not faded. It has only deepened. And as the wonder deepened, so too did the scientific precision with which we probed our galactic neighborhood. Gliese 581c, for all its uncertainties and challenges, became a measuring stick against which future discoveries would be weighed. Every new exoplanet found in the habitable zone of its star system was inevitably compared to Gliese 581c. Was it more Earth-like? Was it closer or farther? Was the atmosphere more stable? Could it host oceans, clouds, seasons? What's especially fascinating is how the questions Gliese 581c raised helped evolve the very definition of Earth-like. Early on, the term was thrown around loosely, often referring to size or location alone. But as observations of Gliese 581c were refined, and it became increasingly clear that it might not be habitable after all, scientists were forced to re-evaluate what truly makes a planet Earth-like. It's not just about being rocky or being the right size. It's about temperature regulation, magnetic protection, atmosphere retention, chemical cycles, and the ability to maintain stable climates over long geological timescales. In this way, Gliese 581c shaped not just discovery, but also philosophy. It encouraged the scientific community to look inward as much as outward. What is life? What do we define as habitable? Would we recognize life if it weren't carbon-based? Could there be forms of life adapted to high-gravity, red-lit environments? Could microbial life exist beneath thick ice sheets on the night side, warmed by geothermal energy or tidal forces? And here lies one of the most critical conceptual contributions of Gliese 581c. It helped push the boundary of speculation toward evidence-based models. Before its discovery, many ideas about extraterrestrial life existed only in the realm of theory or science fiction. But Gliese 581c gave scientists a real laboratory, an actual celestial body around which they could anchor their hypotheses. It catalyzed the development of computer models, atmospheric simulations, and planetary climate studies. It turned speculative conversations into structured, testable frameworks. The planet also led to enhanced investment in telescope design. Observatories such as the James Webb Space Telescope, JWST, the Extremely Large Telescope, YELT, and the proposed LUVOIR, Large Ultraviolet Optical Infrared Surveyor mission were all influenced in part by the questions that planets like Gliese 581c raised. These advanced instruments are designed not only to detect exoplanets, but to analyze their atmospheres in detail. The goal is to look for biosignatures, chemical indicators that suggest biological processes might be at work. Imagine, then, the poetic arc of progress. A relatively small exoplanet orbiting a faint red star becomes the inspiration for multi-billion-dollar scientific endeavors. It was not the most ideal candidate. It was likely too hot, too volatile. Yet it mattered. It mattered deeply because it was one of the first. and its host star, Gliese 581, also became an object of scrutiny. It is a red dwarf, or M-dwarf, and as mentioned earlier, this class of stars is the most common in the Milky Way. In fact, about 75% of all stars are M-dwarfs. That means planets orbiting red dwarfs are likely the most common planets in the galaxy. So understanding one such system, especially one with multiple planets like Gliese 581, could unlock knowledge that applies to millions of other systems. Gliese 581c is just one of at least 6 known planets orbiting the star, although some of those detections remain contested. Among them, Gliese 581d and Gliese 581g have both sparked excitement and debate. Gliese 581d was at one point considered even more likely than 581c to be habitable due to its more temperate position and higher mass, which might allow it to retain a thick atmosphere. Meanwhile, Gliese 581g, if it exists, was thought to lie squarely within the habitable zone, though subsequent studies have challenged its very existence. The uncertainties only emphasize how fine the line is between signal and noise when peering across light years with current instruments. Despite all this, Gliese 581c remains a persistent point of intrigue. In part, this is because the human mind is naturally drawn to the firsts, the trailblazers that open new territories. But it's also because Gliese 581c seems to straddle the threshold between hope and caution. It teaches us that promising signs can be misleading, that being close to Earth-like does not guarantee habitability. It urges us not to leap to conclusions, but to continue refining our models, building better instruments, and asking deeper questions. Consider, too, how Gliese 581c reshaped public imagination. It sparked documentaries, novels, academic papers, and hours of YouTube content, reaching audiences who might never have thought deeply about astronomy. People began to understand that the search for life was no longer speculative fiction. It was empirical science unfolding in real time. And they began to see themselves not as isolated beings on a solitary rock, but as part of a vast cosmic narrative. And still, we return to the basic question: could Gliese 581c support life? The answer is, frustratingly, maybe not. But in that ambiguity lies its power. Because while we may not find life on Gliese 581c, it may still help us find life somewhere else. It may guide us to the next planet, and the next, refining our search criteria along the way. In the process, it teaches us about the resilience of life, the diversity of planetary systems, and the nature of discovery itself. Even if we never set foot on Gliese 581c, even if no spacecraft ever flies by to snap a close-up, the ripples it sent through science, philosophy, and imagination will continue to expand. It is a mirror reflecting our hunger to understand the cosmos and ourselves. In continuing our journey through the significance and mystery of Gliese 581c, we must now delve even deeper, not just into the science, but into the broader implications this planet has had on astronomy, astrobiology, and the ever-shifting perception of humanity's place in the cosmos. The legacy of Gliese 581c is not confined to its own star system. Rather, it acts as a keystone in the grand narrative of exoplanetary discovery. Its influence spreads outward like gravitational waves, felt in every observatory, in every model simulation, and in every conversation that contemplates the probability of alien life. It is essential to understand how Gliese 581c triggered a methodological revolution in planetary habitability studies. Before its discovery, habitability zones were often calculated using simplified models, focusing primarily on the distance from a host star. These Goldilocks zones were defined narrowly. If a planet was not too hot and not too cold, it might be just right for liquid water. But Gliese 581c complicated that narrative. Although it resides close to what was initially considered the inner edge of the habitable zone, later climate models began revealing that distance alone was not enough. The composition of the atmosphere, the planet's albedo, rotational dynamics, magnetic field, and even tectonic activity all play interdependent roles in determining surface conditions. Because of this, Gliese 581c forced scientists to reframe how we define habitability. Its very existence pushed planetary climate modelers to incorporate more parameters, like greenhouse gas concentrations, surface reflectivity, and tidal forces, into their calculations. As a result, definitions of habitable zones became more flexible, more layered, and far more realistic. Earth-like habitability was no longer a simple equation. It became a mosaic of interconnected variables, each playing a vital role in determining the possibility of life. Tidal locking, one of the most talked about factors in Gliese 581c's case, also became a hot topic in the scientific literature. Gliese 581c orbits very close to its red dwarf star. So close, in fact, that it's highly likely the planet is gravitationally locked, showing the same face to its star at all times. This means one side of the planet is perpetually baked in daylight, while the other is cloaked in eternal darkness. Such a situation introduces extreme temperature gradients across the surface and poses challenges to atmospheric circulation. However, more sophisticated simulations have shown that if the atmosphere is dense enough, it could redistribute heat from the hot side to the cold side, creating a stable twilight zone along the Terminator line, the boundary between day and night, where life could potentially thrive. This theoretical possibility opened up entirely new avenues of research. Scientists began to examine the habitability of not just planets within a star's traditional habitable zone, but specifically the Terminator zones of tidally locked worlds. This concept has now become a mainstream consideration in exoplanet research. The impact of Gliese 581c is also psychological. It arrived at a time when exoplanet discovery was just beginning to mature, and it caught the attention of not just astronomers but the public at large. Media outlets seized upon its potential as the second Earth, often with overly optimistic portrayals. While these headlines sometimes oversold the case, they were instrumental in raising awareness and funding for future missions. The public, captivated by the prospect of another Earth-like world, began to demand more from space agencies. This surge in interest helped propel the development of missions like TESS, Transiting Exoplanet Survey Satellite, CHEOPS, Characterizing Exoplanet Satellite, and JWST, James Webb Space Telescope, each designed to build on the questions first raised by early discoveries like Gliese 581c. In this sense, Gliese 581c acted like a celestial ambassador, a planet that galvanized public interest and influenced scientific priorities. Its discovery helped create a cultural shift in how we think about planets beyond our solar system. Before Gliese 581c, exoplanets were often considered novelties. After its discovery, they became destinations. Now let's return to its physical characteristics with even more depth. With a mass about 5 times that of Earth, Gliese 581c is classified as a super-Earth. This term does not imply that it is anything like Earth in terms of conditions. Rather, it merely refers to its size and mass. However, the label itself sparked fascination, encouraging both scientists and the public to wonder, what would it be like to stand on the surface of super-Earth? Gravity would certainly be stronger, perhaps nearly twice that of Earth's. This would affect everything from biological structures to the behavior of fluids. Walking would feel heavy. Jumping would be difficult. Mountains would be lower because high terrain would collapse under its own weight. The atmosphere might be thicker, or it might escape entirely, depending on the planet's magnetic field strength and geological activity. A thicker atmosphere could help in heat distribution, buffering against the temperature extremes of tidal locking. But it could also trap heat more effectively, pushing the greenhouse effect into runaway territory. And what about the light? Gliese 581c orbits a red dwarf star, meaning the light bathing the planet's surface would be tinted red, dimmer than our sun's golden light. Plants, if they evolved, might not be green. Instead, they could be black or dark purple to absorb as much light as possible. This concept has fascinated astrobiologists and artists alike. It challenges our very imagination of what life might look like elsewhere. The composition of the planet's surface remains unknown, but there are clues. If Gliese 581c has a similar density to Earth, it is likely rocky. However, it could also possess large quantities of water or even be a water world, entirely covered by a global ocean. Such planets, sometimes called ocean planets, might lack any solid land masses. Life, if it exists, would be aquatic, and any technological species would need to develop without access to fire or metallurgy. Imagine a civilization born entirely beneath the waves, developing technology using materials shaped by pressure and chemistry alone. But we must also be cautious. Gliese 581c could just as easily be barren, its surface scorched or frozen, its atmosphere toxic or absent. The reality is we simply do not yet have the tools to know for sure. The planet lies 20 light-years away, a vast distance, unreachable by current spaceflight technology. Even if we launched a probe today, it would take tens of thousands of years to arrive. And so, we rely on remote sensing, spectroscopy, and models, tools that grow more sophisticated with each passing year. And yet, even in uncertainty, there is wonder. Gliese 581c symbolizes the boundary between knowledge and mystery. It exists just close enough to tantalize us, but just far enough to remain out of reach. It invites us to dream, to hypothesize, to invest in better technology, and to keep asking, what if? This is why the study of Gliese 581c is more than an academic exercise. It is a call to curiosity. It is a symbol of the human urge to explore, to venture beyond what is known, and to uncover what secrets the universe still holds. In the grand scope of history, Gliese 581c may one day be remembered not for its ability to support life, but for its role in awakening a new era of discovery. And perhaps, someday, with new telescopes orbiting far beyond Earth or stationed on the Moon, or with fleets of autonomous probes racing through the galaxy, we will finally unlock the secrets of Gliese 581c. Perhaps we'll peer into its atmosphere and detect the unmistakable spectral lines of water vapor or methane, or even oxygen. Perhaps we'll discover biosignatures that suggest the planet is, or was, alive. Or perhaps we will find silence. No signs of life. No fertile lands. Just another world among billions, quiet and alone. But even if that is the case, it will not diminish the value of the search. Because Gliese 581c, in all its mystery, is part of our story now. It's a waypoint on the human journey to understand our place in the universe. And that journey is only just beginning. And so the story of Gliese 581c continues, suspended between data and dreams, between the known and the speculated, an enigmatic monument orbiting a dim star in the Libra constellation. The magnitude of its influence on planetary science, speculative astrobiology, and the collective imagination cannot be overstated. But in order to fully grasp the depths of its mystery, we must now explore the vast chain of scientific implications that spiraled from its discovery, not only in terms of what we could learn from it, but in how it transformed the ways we think about planets, stars, and life itself. One of the most profound shifts Gliese 581c instigated lies in how scientists model atmospheres on exoplanets. Because we cannot directly observe its surface, our understanding is mediated by complex simulations. Researchers began constructing thousands of models for Gliese 581c using everything from one-dimensional radiative transfer codes to full-fledged three-dimensional general circulation models, GCMs. These simulations varied temperature, albedo, atmospheric composition, and rotational dynamics. Some hypothesized a runaway greenhouse state. Others imagined an equilibrium of habitability at the twilight belt, while some even entertained the possibility of exotic atmospheric chemistries entirely unlike Earth's. The fascination didn't stop there. Scientists began layering biological plausibility into these simulations. For example, could hypothetical microbial life survive in the high-pressure zones of a dense CO2 atmosphere? Could thermophilic, heat-loving life thrive in the perpetually lit hemisphere, while cryophilic organisms adapted to the dark side? Could a global atmospheric current circulate biosignatures that we might detect from Earth? These theoretical life forms inspired new definitions for the term biosignature itself, not merely limited to oxygen or methane, but expanded to include exotic gases like sulfur dioxide, dimethyl sulfide, or even chloromethane, depending on the planet's chemical makeup. And still deeper questions emerged. How would plate tectonics work on a super-Earth like Gliese 581c? Would its mantle be more viscous, leading to slower tectonic cycles? Or would increased internal heat from gravitational interactions make tectonic activity more vigorous than Earth's? Plate tectonics are essential for carbon cycling, nutrient redistribution, and stabilizing long-term climate. If Gliese 581c lacks tectonic activity, it might be less stable for long-term life, regardless of its atmospheric composition. Then came the geochemical models. Scientists questioned whether the crust of Gliese 581c would resemble Earth's silicate-rich rock, or whether it could be composed of more metallic compounds. Iron content, in particular, has direct implications for magnetic field generation. Without a geodynamo, a convecting molten core, Gliese 581c might not have a magnetic shield, leaving its atmosphere vulnerable to erosion by stellar winds. Red dwarfs, such as Gliese 581, are known for their flaring activity. Without magnetic protection, any early atmosphere could have been stripped away, rendering the surface inhospitable. Yet even with all these potential negatives, Gliese 581c still sparked hope. Why? Because it represented a type of planet that was once thought rare and was now clearly common. Super-Earths are among the most frequently detected exoplanets in our galaxy. Their diversity makes them prime candidates for future study. Gliese 581c wasn't just interesting for its own properties, it was a pioneer. It was a sample of a new class of planet that could be scattered throughout the Milky Way in the tens of billions. It raised the statistical probability that at least some of these worlds might be habitable, if not inhabited. Culturally, this hope took root far beyond the laboratory. Writers, filmmakers, and philosophers latched on a Gliese 581c as a metaphor for cosmic possibility. It became a setting in novels, a destination in video games, and a fixation in speculative documentaries. For many, Gliese 581c was no longer a real place, but a stand-in for everything we want the universe to be: rich, varied, full of mystery, and perhaps full of company. Educational curricula also evolved in response to its discovery. Astronomy textbooks added chapters on super-Earths and habitable zones. Universities offered entire courses on exoplanet climatology and bioastronomy, using Gliese 581c as a case study. Public science institutions, such as NASA and ESA, included it in outreach campaigns to teach planetary science and inspire the next generation of astronomers. It became a symbol, both scientific and poetic, of the boundary between speculation and fact. But what if Gliese 581c was a false signal? Some researchers have questioned whether the early orbital data were interpreted correctly. Gliese 581 is a red dwarf, and red dwarfs often exhibit star spots, magnetic blemishes on their surfaces that can interfere with radial velocity measurements. These measurements are crucial for detecting exoplanets and calculating their orbits. Some reanalyses of the data have suggested that what was thought to be Gliese 581c may have actually been stellar noise. In 2014, a controversial paper argued that both Gliese 581g and Gliese 581d might be artifacts, though Gliese 581c remained more robustly supported. Still, this controversy sparked new advancements in data processing and statistical analysis. The techniques used to confirm or refute Gliese 581c's existence became more refined, more resistant to stellar interference, and more rigorous overall. That's another of Gliese 581c's enduring legacies. Its role as a crucible for method refinement. The debates it inspired forced the exoplanet community to elevate its standards, ensuring that each new planet reported would be subjected to more sophisticated scrutiny. It was a scientific stress test, and through it, the field matured. On a more philosophical note, Gliese 581c invites us to re-evaluate our definition of Earth-like. Early reports described it that way simply because it was rocky and within a certain distance from its star. But over time, we've realized how shallow that comparison was. Being Earth-like is not just about size and distance. It's about climate, atmospheric composition, geological activity, magnetic shielding, and the capacity to support complex chemical cycles over billions of years. By that metric, Gliese 581c may be far less Earth-like than we initially hoped. And yet, that disappointment turned into something greater, a deeper, more nuanced understanding of what habitability truly means. This reframing also changed how we prioritize future targets for exploration. Missions like JWST, the Nancy Grace Roman Space Telescope, and the proposed LUVOIR, Large UV Optical Infrared Surveyor, now use more detailed criteria when selecting exoplanetary candidates. These criteria were sharpened by the experience of analyzing Gliese 581c. It taught us that habitable zone is a starting point, not a guarantee. That knowledge now guides how we use precious telescope time and where we aim our most sensitive instruments. Even now, new ideas continue to emerge. Some scientists propose that planets like Gliese 581c could harbor subsurface life in protected niches, beneath thick ice, in deep ocean vents, or within porous rock warmed by geothermal activity. These hidden biospheres might be undetectable from afar, but could still represent thriving ecosystems. If Gliese 581c does have a subsurface ocean, shielded from the extremes of its surface, it might resemble icy moons like Europa or Enceladus, which are among the most promising places to find life in our own solar system. Others suggest that Gliese 581c, even if lifeless, might still provide insights into planetary formation. Its position in the Gliese 581 system, its resonance with neighboring planets, and its interaction with stellar tides could help us understand the gravitational dance of planetary systems. This in turn might help us understand why our own solar system ended up the way it did, with one planet teeming with life and the rest seemingly barren. Gliese 581c is no longer just a name on a list of exoplanets. It's a milestone, a scientific lesson, a cultural touchstone. It embodies the transition from hopeful guesswork to rigorous science, from oversimplified models to complex simulations, from blind optimism to reasoned curiosity. Its very ambiguity, its failure to live up to early hopes, became its strength. In not being the Earth twin we dreamed of, it taught us how to better look for the next one. And so we keep looking, armed with better tools, clearer criteria, and deeper questions. The light from Gliese 581 still reaches our telescopes, whispering secrets carried over 20 years of travel across the void. And somewhere in that light, encoded in its flickers and shadows, may lie the answers we seek, not just about that distant planet, but about all the worlds yet to be discovered. The tale of Gliese 581c does not end with scientific data or revised expectations. In many ways, it begins anew with every technological advance that improves our ability to peer deeper into the cosmos. The tools we use to observe exoplanets, spectrometers, interferometers, coronagraphs, have evolved drastically since the planet's discovery in 2007. And each advancement reopens the case of Gliese 581c with fresh eyes, allowing us to ask new questions, test new hypotheses, and consider new possibilities. One of the most promising developments has been the improvement in direct imaging techniques. Although Gliese 581c is far too distant and too close to its parent star for us to currently image directly, the pursuit of such capabilities has led to the creation of star shades, massive, flower-shaped spacecraft that block starlight to enable telescopes to view orbiting planets. These innovations will one day allow us to directly analyze the reflected light from exoplanets like Gliese 581c, giving us invaluable data about surface composition, cloud cover, and potentially even vegetation like biosignatures. Until that day arrives, scientists have turned their attention toward spectroscopy as the next best tool. When a planet transits in front of its star, as Gliese 581c does not, unfortunately, it creates an opportunity to study its atmosphere by analyzing the starlight that filters through it. Even without transits, astronomers can analyze how a planet's gravity tugs on its star or how light reflects off the planet during different orbital phases to tease out details about the planet's properties. Though Gliese 581c does not transit, similar techniques have been used in attempts to deduce properties of the other planets in the system, which helps build a broader contextual model. These indirect methods have sparked new generations of astronomers to take interest in the field. In universities around the world, graduate students run atmospheric models based on Gliese 581c's mass, orbital data, and estimated stellar flux. These students craft simulations of what it might be like to stand on the surface of the planet, if a surface exists at all. Some simulations depict a hellish world of superheated rock and carbon dioxide, a suffocating super-Earth caught in the grasp of a greenhouse runaway. Others envision a thin strip of habitability along the Terminator line, the band between night and day, where temperatures may be stable enough to support life or at least liquid water. Yet despite all this, one cannot help but return to a central, haunting question. What would we see if we could look directly at Gliese 581c with perfect clarity? Would it show signs of oceans, continents, and clouds? Or would it appear as a scorched, lifeless ember circling a faint red star? This question isn't just about Gliese 581c. It's about the kind of universe we inhabit. Is it teeming with life, scattered across billions of worlds? Or is life so rare that even the most promising planets remain sterile? This existential question has become a touchstone for the philosophical arm of astrobiology. Scientists and thinkers alike have turned to Gliese 581c in discussions of the Fermi paradox. If life is common, why haven't we heard from it? Some argue that perhaps planets like Gliese 581c once hosted life, but lost it to atmospheric collapse or stellar flaring. Others speculate that life does exist, but remains hidden, primitive, or simply uninterested in interstellar communication. Either way, Gliese 581c remains a mirror, not just for our scientific hopes, but for our philosophical longings. Artists have found inspiration here too. The idea of Gliese 581c has given rise to countless speculative illustrations, depicting alien terrains bathed in a dim red glow or dramatic mountain ranges backlit by a swollen, crimson sun. Science fiction writers set their stories here, using Gliese 581c as a canvas for imagining what it might mean to start over on another world, to survive in extreme conditions, or to make first contact with an alien intelligence. This blending of science and art reinforces how deeply the planet has embedded itself into the human imagination. Educational platforms, such as planetariums and digital exhibits, now regularly include Gliese 581c in their presentations, using it to help audiences understand how exoplanet science works. Teachers use it to explain orbital mechanics, tidal locking, and the Goldilocks zone. Documentaries profile as one of the stepping stones in humanity's search for another Earth. The public, once unfamiliar with exoplanets, now follows missions like TESS, JWST, and Plato because of the curiosity first sparked by Gliese 581c. The planetary system it inhabits has also drawn renewed attention. Gliese 581b, C, D, and E form a complex gravitational web with possible resonances and long-term orbital stability that still challenge astrophysical models. The presence of multiple planets around a relatively quiet red dwarf raised hopes that such stars, once considered too hostile, might actually be ideal for hosting planetary systems. And since red dwarfs are the most common type of star in the Milky Way, this realization dramatically expanded the estimated number of potentially habitable planets. Even the smallest variations in orbital eccentricity can dramatically affect climate stability. Some researchers have simulated scenarios where Gliese 581c oscillates between icehouse and greenhouse states over thousands of years, akin to Earth's Milankovitch cycles. This possibility raises intriguing questions about the evolution of life on such a world. Would life develop resilience to these climate shifts? Could a biosphere evolve in rhythm with the orbital dance, surviving through long ages of frost and fire? But even if Gliese 581c proves sterile, its influence endures. It marked a turning point, a moment when the search for other Earths became not just feasible, but urgent. It opened the doors for broader conversations about planetary habitability, synthetic biology, interstellar travel, and the future of humanity. It challenged our understanding of what it means to be Earth-like, and in doing so, helped mature the entire field of exoplanetary science. We now know that planets like Gliese 581c are only the beginning. Since its discovery, hundreds of other potentially habitable worlds have been found, many with better chances for habitability. Planets like Kepler, 186f, TRAPPIST, 1e, and Proxima Centauri b have captured headlines and imaginations. But Gliese 581c retained a unique place in history. It was among the first. It was the spark. It turned possible into real. And no matter what we learn in the future, that legacy will never fade. Still, new frontiers remain. Could future probes someday visit the Gliese system? Could a fleet of laser-propelled nanocraft, like those envisioned in the Breakthrough Starshot initiative, be sent to study its planets directly? These are no longer science fiction. They are engineering challenges awaiting breakthroughs. In the background, Gliese 581c waits, quiet, distant, and unresolved. Its red light continues to shine across the void, touching the lenses of our most powerful telescopes, teasing us with the secrets it may hold. It is not the answer. It is the question, and that makes it priceless. Gliese 581c, despite its distance of 20.4 light-years from Earth, represents a close neighbor in astronomical terms. That proximity amplifies its significance because it offers a rare opportunity to refine our detection techniques and build a roadmap for future interstellar missions. Though unreachable by current spacecraft, it remains within theoretical range of future technology, and that possibility continues to fuel efforts in both scientific and engineering communities. The concept of sending probes to Gliese 581c, once a far-fetched dream, has been entertained more seriously in recent years. Initiatives such as Breakthrough Starshot, backed by luminaries like Stephen Hawking and Yuri Milner, propose launching tiny spacecraft powered by high-powered lasers to reach nearby star systems within a human lifetime. Though Gliese 581 isn't the first target, Alpha Centauri being the primary candidate, technological success in such missions could eventually extend the scope of humanity's reach. The question remains, what kind of data could we retrieve if we sent even a single gram of matter to fly past Gliese 581c? Miniaturized sensors aboard such craft could collect basic data on radiation levels, magnetic fields, stellar wind interactions, and more. If a fleet of such probes were directed to fly past Gliese 581c and capture even the most rudimentary images or spectroscopic readings, the scientific value would be extraordinary. Even a blurry image of the planet's surface would carry profound implications, confirming theories or challenging assumptions about its albedo, potential atmospheric haze, or terrain variation. This makes Gliese 581c not just an object of remote curiosity, but a potential destination in our interstellar aspirations. This shift in thinking, from passive observation to active exploration, marks a defining transition in the field of astronomy. It also places a philosophical weight upon our shoulders. If we have the tools to reach another world, even indirectly, how should we proceed? What ethical and technological frameworks must we develop to guide humanity's first interactions with alien systems? Even before we reach Gliese 581c physically, we are working toward a form of virtual proximity. Simulations using supercomputers are allowing us to recreate its likely environment with increasing fidelity. Programs integrate known physical parameters, mass, orbital eccentricity, estimated stellar flux, and then run countless variations to produce hypothetical climates. Some of these simulations are immersive, allowing researchers to virtually walk across the terrain, observe dynamic weather systems, and experience the subtle shifts in sky color as seen from a world orbiting a red dwarf. The visuals generated from these simulations are not just for show. They help refine hypotheses about where habitability might realistically emerge. For instance, if the planet does have an atmosphere, what are the odds of persistent high winds resulting from the temperature differential between the perpetually lit side and the dark side? Would those winds circulate heat efficiently or create destructive atmospheric instability? How deep might an ocean be on the Terminator line? And would ice dominate the dark hemisphere? Or would geothermal heat prevent freezing entirely? These questions are driving research into planetary circulation models, tidal effects, and oceanic stability, all of which have implications beyond Gliese 581c. By studying this world, we're better preparing to understand a broader class of tidally locked planets, which may turn out to be some of the most common types of habitable planets in our galaxy. It's also worth considering how Gliese 581c has influenced science communication. At a time when many people were still unfamiliar with the term exoplanet, its discovery acted as a public gateway to the broader world of space science. The planet became the subject of countless science news articles, television specials, and public lectures. Animations showed what it might look like. Infographics compared it to Earth. Headlines speculated about alien life. Even now, over a decade and a half later, Gliese 581c is often one of the first planets mentioned in discussions about exoplanetary habitability. In this way, it has taken on a cultural identity. It is no longer merely a celestial object defined by mass and radius. It is a symbol, a scientific milestone, a muse for imagination, a puzzle for engineers and physicists. In classrooms around the world, students learn about the concept of the habitable zone using Gliese 581c as a primary example. In research papers, it is cited as a progenitor of interest in M-dwarf systems. And in speculative fiction, it appears as a setting for first contact, colonization, or cosmic revelation. The continuing discussion surrounding Gliese 581c also reflects the dynamism of science. Initially hailed as a potentially habitable super-Earth, later reconsidered as likely too hot, and then revisited again with fresh models and analysis. It embodies the evolving nature of scientific understanding. It teaches us humility, that no data point is absolute, no model infallible, and no conclusion final. Every new piece of data, every innovation and observation reshapes what we believe to be true. This scientific humility is especially important when considering the biases that exist in our own expectations. We naturally compare other planets to Earth, seeking similar temperatures, atmospheres, and gravity. Yet Gliese 581c may teach us that habitability can wear many masks. Perhaps life could thrive in subterranean oceans shielded from stellar flares. Perhaps it could exist as microbial colonies that live on the dark side, powered by geothermal vents. Or perhaps Gliese 581c teaches us that life is not present everywhere it can exist, that chance and history are just as important as chemistry and physics. Either way, its role in the ongoing search for life remains vital. It reminds us that the search is just beginning, that each exoplanet we discover adds another brushstroke to a galactic canvas we've only begun to sketch, and that no matter how many worlds we find, Gliese 581c will always be remembered as one of the first that made us truly look outward, not just with telescopes, but with hope. Hope that we are not alone. Hope that the cosmos is filled with diversity. Hope that the things we build, our machines, our models, our methods, can bridge the incomprehensible distances of space to deliver truth back to us. Hope that this one small point of light in the sky may one day answer a question humanity has asked since we first looked upward. Is there anyone else out there? In its silence, Gliese 581c continues to challenge us. And in our persistence, we answer back, not with certainty, but with curiosity. And perhaps, in the end, that is the more important of the two. This curiosity, relentless and unyielding, is what propels the scientific community to continue studying Gliese 581c despite the passage of time and the flurry of newer discoveries. The exoplanet's early fame does not mean its importance has faded. On the contrary, its role as a case study for planetary science has only deepened. With every new tool and refined technique, we re-examine Gliese 581c like archaeologists returning to a historically rich site with better instruments. And each time, we uncover another layer of insight that not only redefines our understanding of this single planet, but also informs the broader search for habitable worlds. One of the most enduring challenges in the study of Gliese 581c is reconstructing its atmospheric conditions. Since we cannot directly observe its atmosphere with current telescopes, we are left to infer its properties based on stellar activity, planetary mass, orbital position, and computer models. We imagine scenarios, a thick carbon dioxide blanket similar to Venus, which could trap heat and create a runaway greenhouse effect, or perhaps a thinner, more tempered atmosphere where water could condense and support cloud systems. Each model is run through simulations thousands of times, with small adjustments made to variables such as surface reflectivity, greenhouse gas composition, and stellar radiation intensity. Yet even in this uncertainty lies progress. With each simulation that rules out a particular combination of atmospheric elements, we get closer to defining a probabilistic envelope for Gliese 581c's climate. We begin to understand which combinations are more likely to exist, which extremes are improbable, and which possibilities remain tantalizingly unresolved. These efforts also improve the climate models we use for other exoplanets. By solving Gliese 581c, in a sense, we fine-tune our approach to thousands of others like it. Perhaps most captivating is the idea that Gliese 581c may host a form of life completely alien to our expectations. Not carbon-based, not oxygen-breathing, not water-dependent. Something fundamentally different, shaped by its own evolutionary pressures. A biosphere adapted to dim red light, to intense magnetic storms, to a tidally locked world where the concepts of day and night lose all meaning. On such a world, photosynthesis might not even occur in the way we know it. Life could absorb infrared light or use geothermal heat as its energy source. Chemosynthesis, rather than photosynthesis, might be the driving metabolic force. These musings aren't just science fiction. They're plausible extensions of real biochemical pathways we've seen here on Earth, especially in deep-sea hydrothermal vent ecosystems. Life, as it turns out, is staggeringly adaptable. The extremophiles of our own world, organisms that thrive in boiling acid, frozen salt lakes, or vacuum-like conditions, demonstrate that biology is less fragile than we once thought. And if life can exist in Earth's harshest corners, then it becomes a legitimate question whether similar processes could take root on Gliese 581c under even more exotic circumstances. Another overlooked aspect of Gliese 581c's story is the philosophical reflection it provokes. The planet serves as a mirror, forcing us to confront what we mean by habitability. Are we searching for another Earth, or are we seeking the very notion of life, regardless of its form? When we say a planet is habitable, do we mean it is suitable for humans, or that it could support any kind of living system? These distinctions are vital, because if we narrow our definition too much, we might miss signs of non-Earth-like life. But if we broaden it too far, we risk attributing habitability to worlds that are fundamentally hostile. This tension between specificity and openness in our search criteria has shaped the way exoplanets are evaluated today. Habitability indices, which rank planets based on their likelihood to support life, now incorporate multidimensional metrics that go beyond distance from a star. They include factors such as stellar type, orbital stability, planetary density, atmospheric retention potential, and more. Gliese 581c helped usher in this era by highlighting the complexity of the question, could this planet support life? And as our tools improve, we inch closer to answering it. With next-generation space telescopes, such as the James Webb Space Telescope already in operation and future missions like the Extremely Large Telescope and LUVOIR, Large UV/optical/IR surveyor, on the horizon, we will soon have the capability to directly analyze the atmospheres of exoplanets like Gliese 581c. These instruments may detect biosignatures, molecular traces of life such as methane, ozone, or even industrial pollutants. Even a faint whiff of such signals would provoke seismic shifts in both science and society. The implications would be staggering. A confirmed biosignature from Gliese 581c would force a rethinking of biology, theology, philosophy, and even law. We would have to grapple with new questions. What rights, if any, does alien life possess? How do we ethically study it? Could communication be possible, or even desirable? Would we attempt contact, or quarantine ourselves in fear of contamination or conflict? These questions, though speculative, are increasingly taken seriously by ethicists and policymakers. A discovery on Gliese 581c wouldn't just be scientific, it would be civilizational. And perhaps that is the most profound legacy of Gliese 581c. Not the specifics of its mass or orbit or even its potential oceans, but the role it has played in awakening our collective imagination. It has become a fixed point in the unfolding story of cosmic exploration. Like the first photograph of Earth from space, it forces us to look at ourselves differently, not as isolated beings, but as members of a broader galactic community that we are only beginning to discover. The journey toward Gliese 581c, though so far consisting only of photons and theory, has already changed us. It has expanded our vision, deepened our questions, and reaffirmed our shared drive to explore. It stands as a reminder that the unknown is not a void, but a canvas, waiting to be explored, understood, and ultimately connected with. The deeper we gaze into the universe, the more Gliese 581c reminds us that perhaps the most important discovery of all is not that we might find life out there, but that the search for it reveals the deepest truths about who we are here. Gliese 581c continues to be more than just an object of astronomical curiosity. It is a philosophical frontier, a symbol of humanity's evolving relationship with the cosmos. In the earliest days of its discovery, when scientists first confirmed the presence of an Earth-like world in the habitable zone of a distant red dwarf, the global reaction was electric. Headlines were ablaze with excitement. The scientific community buzzed with hypotheses, and even casual observers were swept up in a wave of hopeful speculation. The planet wasn't just a dot on a telescope's viewfinder. It was a beacon, a tantalizing possibility that we might not be alone in the universe. But the real legacy of Gliese 581c may not lie in what it is, but in what it triggered. It marked the beginning of a new phase in exoplanetary science, in which the focus shifted from mere detection to detailed characterization. Prior to its discovery, finding a planet outside our solar system was itself a monumental event. But Gliese 581c taught us to ask more refined questions. Is the planet rocky or gaseous? What is its temperature range? Could it hold liquid water? What is the nature of its atmosphere? Could life thrive there? The act of seeking answers to these questions revolutionized the tools and methods used in astronomy. Spectroscopy, for example, evolved from a primarily stellar tool into an exoplanetary one. Astronomers began to use minute differences in starlight absorption to infer the chemical composition of planetary atmospheres. These techniques have been applied not only to Gliese 581c, but also to hundreds of other exoplanets, expanding our understanding of what is possible in planetary systems. Simultaneously, theoretical modeling saw a renaissance. Complex simulations now explore how a planet's rotation, obliquity, internal heat, and geological activity could affect its climate and potential habitability. Models have examined what Gliese 581c would look like under a variety of scenarios. One where it has a thick, Venus-like atmosphere, another where it has a balanced greenhouse effect like Earth's, and even one where it has no atmosphere at all, leaving it to the mercy of space's deep freeze. Each of these models feeds into the broader scientific conversation. They provide valuable data points, even when they rule out habitability. Knowing that a certain planetary mass combined with a close orbit to a red dwarf may lead to runaway heating is as useful as confirming habitability, because it helps refine our criteria, making future searches more efficient and informed. In fact, Gliese 581c also contributed indirectly to another critical area of exoplanetary study: stellar activity. Red dwarfs like Gliese 581 are known for being volatile, often emitting flares of high-energy radiation. These flares can strip away planetary atmospheres and pose a serious challenge to life as we know it. Because Gliese 581c is in such close orbit, it is more susceptible to these outbursts. Understanding how red dwarfs behave and how their emissions interact with planetary magnetospheres has become a field of study in its own right, and Gliese 581c has served as a prime subject. This deepening complexity also began to influence the public imagination. Gliese 581c was mentioned in documentaries, science fiction books, and classroom discussions. It made its way into pop culture as a symbol of cosmic possibility. The fact that such a world could exist, tantalizingly close on a cosmic scale, challenged people to reframe their understanding of the universe. No longer was Earth the singular bastion of life. Now, it was part of a broader galactic ecosystem whose members were only just being identified. More recently, advances in machine learning and artificial intelligence have entered the fray. AI models trained on known planetary data can now predict likely characteristics of planets like Gliese 581c, offering insight into its potential terrain, temperature zones, and even weather patterns. Some models can simulate what the planet might look like visually, given different atmospheric compositions. These visualizations, though speculative, help ground the data in something relatable, giving both scientists and the public a visceral connection to these distant worlds. Despite newer and arguably more promising candidates being discovered, such as the TRAPPIST-1 system, Gliese 581c continues to occupy a unique place in the exoplanet pantheon. It remains one of the first truly Earth-like worlds ever found, and as such, it serves as a benchmark. Every new discovery is, in some way, compared to Gliese 581c. Is it larger or smaller? Hotter or colder? Closer or farther from its star? Is its sun more stable or more violent? Gliese 581c's influence echoes through the exoplanetary research community like the reverberations from a bell. Long after the initial strike, the vibrations persist. And then, of course, there is the question of human visitation. While we are nowhere near being able to travel to Gliese 581c, the very notion has been contemplated in serious forums. Concepts like Breakthrough Starshot, a project aiming to send microprobes to nearby stars using light sails, hint at the kind of ingenuity that might someday make such exploration possible. Though Gliese 581c is far beyond the reach of current Starshot ambitions, it embodies the spirit that fuels such projects. The belief that distance is a challenge, not a barrier. It's fascinating to imagine what a mission to Gliese 581c would look like. Would we send robotic explorers first, outfitted with advanced AI capable of autonomous decision-making? Would these machines be equipped with sensors designed to detect not just water or oxygen, but biosignatures more exotic than anything we've seen? Would we construct orbiters to map the planet's magnetic fields, geologic features, and atmospheric dynamics? Will we try to land on its surface? And if so, what will we find there? Would the landscape be scorched and barren, a lifeless twin to Venus? Or would it be rich with alien ecosystems adapted to conditions no Earth creature could survive? Would we find oceans under perpetual twilight, forests of silicon-based flora, or skies tinted a color we have no name for? Would there be signs, not of life, but of intelligence? Signals etched in radio waves, artifacts scattered across the terrain, or patterns too ordered to be natural? These are the questions that animate the mind, that keep scientists, writers, and dreamers awake at night. Gliese 581c is not just a planet. It's a question mark hanging in the sky, a challenge to explore further and think deeper. And in that way, Gliese 581c is more than a place. It's an idea, an enduring symbol of humanity's search for its cosmic context. It reminds us that even in the void, even in the cold silence between stars, there are places that reflect something familiar back at us. Not a mirror image, but a distorted echo, a suggestion that we are not alone in our capacity to be. So we continue to listen. We point our telescopes. We refine our models. We argue, we hypothesize, and we dream. Because somewhere out there, orbiting a dim red sun, is a world that, once upon a time, whispered, "You are not the only ones." We're still listening. Not just to the faint gravitational wobbles and dimming of starlight that hint at the existence of distant worlds like Gliese 581c, but to the deeper meaning that such discoveries stir in the collective human psyche. The idea of Gliese 581c has reached beyond astronomy. It's a fixture in the new mythos of exploration, a modern chapter in the story that began with ancient sailors peering beyond the horizon. Except now, the sea is infinite, and the horizon is measured in light years. Gliese 581c lies about 20.4 light years away from Earth, nestled in the constellation Libra. Though that distance seems manageable in a cosmic context, it's an almost inconceivable challenge for us in practical terms. Even traveling at the speed of the fastest spacecraft ever launched by humans, it would take tens of thousands of years to get there. But this barrier hasn't deterred thinkers, engineers, and futurists from proposing interstellar probes and generational starships designed to reach systems like Gliese 581. The planet itself is thought to be about 1.5 times the radius of Earth and around 5 times as massive, putting it into the category of super-Earths. This size implies a much stronger gravity than we experience on Earth, and such gravity would influence everything. The height of mountains, the density of the atmosphere, even the way water flows. Imagine walking on a world where every step feels as if you're carrying another person on your back, where you can't jump high, but where your muscles would become extraordinarily efficient if you adapted over time. These kinds of physiological implications have captured the imagination of space biologists and science fiction creators alike. Early excitement about Gliese 581c stemmed from its position within its star's habitable zone, also called the Goldilocks zone, where conditions might allow liquid water to exist. But later studies have suggested the situation is far more nuanced. Gliese 581c is very close to its parent star, Gliese 581, which is a red dwarf. This type of star emits less energy than our Sun, but the planet's proximity compensates for this, making it receive more energy than Earth does. In fact, some estimates suggest that Gliese 581c receives about 30% more stellar energy than Venus does from the Sun, suggesting it may suffer from a runaway greenhouse effect, rendering the surface scorching and uninhabitable. Yet, the story doesn't end there. One of the most intriguing aspects of Gliese 581c's potential habitability lies in the possibility of tidal locking. Because it is so close to its star, gravitational forces may have caused one side of the planet to always face the star, perpetual daylight, while the other side is trapped in eternal night. This might sound like a death sentence for habitability, but it could actually produce a fascinating middle ground. The Terminator line, the twilight region between the light and dark hemispheres, could theoretically have temperatures mild enough to support liquid water and potentially life. The idea of a habitable ring encircling the planet where day meets night has become a focal point in speculative discussions. Could this narrow band harbor an atmosphere that circulates heat efficiently from one side of the planet to the other? Could oceans exist along this line, perhaps fed by glacial melt from the dark side or clouds condensed from the warm side? Could life evolve in such a unique zone? And if so, what would it look like? What makes this so captivating is that we've never seen anything like it in our own solar system. Every planet we know spins on its axis, distributing day and night fairly evenly. But on a tidally locked world like Gliese 581c might be, ecosystems could be divided by extremes. The sun-facing side may be a scorched desert, while the dark side is a frozen wasteland. Life, if it exists, would have to adapt to conditions unlike any on Earth, possibly evolving mechanisms to cope with low light, extreme temperature gradients, and intense atmospheric winds caused by heat imbalances. Atmosphere itself is another layer of intrigue. If Gliese 581c does have a dense atmosphere, it could act like a thermal blanket, redistributing heat from the day side to the night side and potentially evening out the climate across the planet. But if the atmosphere is thin, those temperature differences could be brutal, possibly even violent, with supersonic winds and chaotic weather systems. The chemical composition of such an atmosphere would be critical. A thick carbon dioxide envelope, similar to Venus, would create an inhospitable hellscape. But a balanced mixture of nitrogen, oxygen, and water vapor could create Earth-like conditions in select regions. Scientists are currently working on models to determine what atmospheric profiles are even theoretically possible for Gliese 581c, given its size, mass, and stellar radiation. Then comes the magnetic field, a key player in planetary habitability. A magnetic field protects a planet's atmosphere from being stripped away by stellar winds. Earth's field is generated by the motion of its molten iron core. Would Gliese 581c have a similar geodynamo? Its higher mass suggests a larger core, and if that core is active, it could indeed generate a protective field. But we don't know for sure. Without a magnetic field, the planet's atmosphere could have been stripped over billions of years, leaving it barren. Interestingly, the surrounding Gliese 581 system has several other planets, some of which have also been candidates for habitability. For example, Gliese 581d was once thought to lie within the outer edge of the habitable zone, while Gliese 581g was announced as potentially the most Earth-like planet ever found, though its very existence is still under dispute. The fact that Gliese 581c was discovered within a multi-planet system raises fascinating questions about planetary formation and migration. Did these planets form where they are, or were they gravitationally nudged into new orbits by each other or by their host star? These dynamics shape everything from orbital resonance to planetary climate cycles. The search for answers is driving innovation. Space telescopes like the James Webb Space Telescope and the Future Habitable World Observatory are being designed with instruments capable of detecting biosignatures, chemical traces that may indicate life. These include oxygen, methane, water vapor, and even more complex compounds like chlorophyll derivatives. While Gliese 581c might not currently be in line for such detailed study due to its likely harsh environment, it remains a template for what to look for and how to look for it. The legacy of Gliese 581c is already etched in the astronomical canon. It catalyzed a paradigm shift in exoplanet research, from a focus on discovery to a focus on characterization and habitability. It inspired thousands of scientific papers, countless media stories, and even messages sent into space by hopeful humans reaching across the void. The planet has received radio signals as part of active SETI experiments, humanity's earliest attempt to say, "Hello, are you there?" to the cosmos. While no response has returned, the act itself is profound. It's a testament to our desire not just to explore, but to connect. And so, Gliese 581c remains silent, at least for now. But its silence is not emptiness. It's the space into which we project our hopes, our fears, our questions, and our resolve. It's a world that forces us to ask, what is life? What is home? What lies beyond our sky? As telescopes grow sharper, as probes fly farther, and as our understanding deepens, we may one day get the answers we seek. Not just about Gliese 581c, but about ourselves. We continue our journey with Gliese 581c, not merely as a scientific curiosity, but as a mirror through which humanity views its own existential questions. Its allure lies not just in what it is, but in what it represents, a beacon in the cosmos pulling at our imagination, our intellect, and our thirst for discovery. It is one of the earliest and most compelling examples of an exoplanet that challenged our assumptions, expanded our horizons, and redefined the boundaries of possibility. At its core, Gliese 581c has become a philosophical object as much as a physical one. The moment it was discovered, it altered the landscape of planetary science. Before it, exoplanets were largely gas giants, massive and inhospitable. But Gliese 581c was different. It was a super-Earth. This term, though technical, invokes something more poetic, the idea that another Earth, another version of our home, might exist out there. It wasn't the first exoplanet to orbit in its star's habitable zone, but it was among the earliest to do so in a way that caught global attention. It showed that the idea of a second Earth was not science fiction. It was science in progress. To fully appreciate the impact of Gliese 581c, we must understand its place in exoplanetary science. Discovered in 2007 by Stefan Udry and his team using the HARP spectrograph on the ESO 3.6-meter telescope at La Silla Observatory in Chile, Gliese 581c became a media sensation. The planet was found through the radial velocity method, a technique that detects wobbles in a star's motion caused by the gravitational tug of orbiting planets. These wobbles, while minute, are detectable with incredibly precise instruments. From the subtle shifts in starlight, astronomers calculated the mass and orbit of Gliese 581c. This method, however, comes with limitations. Radial velocity does not directly reveal a planet's size, only its minimum mass. Without transit data, when a planet passes in front of its star and dims the star's light, we are left to estimate other properties using models. This ambiguity has fueled debates for years. While we know Gliese 581c is more massive than Earth and orbits its star every 13 Earth days, we do not know definitively whether it has an atmosphere, what it's composed of, or whether it is liquid water. Much of what we assume about Gliese 581c comes from indirect inferences and analogies to known planetary behavior. One of the fascinating features of the Gliese 581 system is the nature of its host star. Gliese 581 is a red dwarf. A type of star smaller and cooler than our sun. Red dwarfs are the most common stars in the galaxy, making up roughly 75% of all stars in the Milky Way. Their abundance means that if life can exist around red dwarfs, the chances of life in the universe increase dramatically. However, red dwarfs are also known for their instability. Many emit strong stellar flares and radiation bursts that can strip away planetary atmospheres and sterilize surfaces. The question of whether Gliese 581 is a quiet or active red dwarf is still debated. Some studies suggest it's relatively stable, which would be good news for planetary habitability. Others argue that intermittent flaring could have eroded any chance for life. Despite the uncertainty, the scientific community quickly recognized the importance of Gliese 581c. It became a proving ground for planetary modeling. Researchers constructed climate simulations, habitability indices, and atmospheric scenarios to explore what kinds of conditions might exist. Would it have a thick atmosphere like Venus, resulting in extreme heat? Could it have clouds that reflect stellar light, keeping the surface cooler? Could geothermal activity provide heat to subsurface oceans, Much like Jupiter's moon Europa, each model brought us closer to understanding not just Gliese 581c, but the wider spectrum of what habitable worlds might look like. The implications stretch far beyond the Gliese 581 system. Studying Gliese 581c has led to refinements in exoplanet classification. The term habitable zone itself has evolved. No longer a static ring, it is now seen as a flexible region dependent on multiple factors: stellar output, planetary albedo, atmospheric composition, and geological activity. Gliese 581c taught us that habitability is not binary. It's a complex, layered probability space. It also influenced the way we search for life. Scientists now focus not just on Earth-like conditions, but on life as we don't know it scenarios. The possibility of life thriving in extreme environments has opened the door to a broader definition of what it means for a world to be habitable. Gliese 581c may not have oceans and forests, but could it harbor extremophiles? Could microbial life survive in subterranean niches or in the shadowed crevices of its Terminator line? These questions are not idle speculation. They guide the design of instruments, mission parameters, and observation targets. Gliese 581c's story is also a cautionary tale in the annals of science communication. When it was first discovered, many headlines touted it as a second Earth. The excitement was understandable, but it led to misconceptions that linger even today. The planet is not Earth 2.0. Its high mass, potential tidal locking, and possible atmospheric instability make it a very different environment. Yet, these differences are what make it valuable. Gliese 581c reminds us that the universe is not obliged to mirror Earth. The search for life is not a search for Earth clones, but for viable alternatives, worlds that, in their uniqueness, might still harbor life. Technologically, Gliese 581c pushed the boundaries of what our instruments could detect. The precision of the HARPS spectrograph, capable of measuring velocity changes of less than 1 meter per second, was a leap forward. Since then, instruments like Espresso and the upcoming YELT, extremely large telescope, are taking this precision even further. Each improvement allows us to revisit earlier discoveries with fresh eyes. Perhaps one day, we will resolve the ambiguities that still cloak Gliese 581c in mystery. Philosophically, Gliese 581c has had a profound impact. It forced us to confront the possibility that we are not alone, not just in terms of life, but in terms of habitable real estate. It challenged the anthropocentric assumption that Earth is the template for life. It made us ask whether life is rare or common, and what conditions are truly necessary for it to emerge. It reminded us that the universe is vast, and that our understanding of life must be equally expansive. We dream of one day sending probes to Gliese 581c. The concept of interstellar travel, once confined to science fiction, is now a topic of serious discussion. Projects like Breakthrough, Starshot envision tiny, laser-powered spacecraft traveling at a fraction of the speed of light. These probes, if realized, could reach nearby star systems within a human lifetime. Although Gliese 581 is not the closest target, the technology being developed could one day make missions to such distant worlds feasible. Even before we reach it physically, we may study Gliese 581c in unprecedented detail using space-based observatories. Missions like LUVOIR and HabEx, currently in the proposal stages, aim to directly image exoplanets and analyze their atmospheres for biosignatures. A successful detection of oxygen, methane, or water vapor on Gliese 581c would reignite interest and redefine our understanding of life's potential in the cosmos. The journey continues as it must. Gliese 581c is not the end point, but a waypoint, a marker along the path of discovery. It has taught us to look deeper, to question assumptions, and to embrace complexity. It has sparked debates, inspired dreams, and expanded the horizon of the possible. And still it waits, a world circling a quiet star, bathed in red light, wrapped in mystery, waiting for us to find a way to see it not just as data points and models, but as a place, a world with skies and winds, heat and cold, maybe even dreams of its own. As we resume our exploration of Gliese 581c, it's essential to acknowledge just how deeply this one exoplanet has woven itself into the broader tapestry of astronomical research and philosophical thought. It is a reminder that even the smallest hints of Earth-like potential beyond our solar system can send ripples across scientific communities, media platforms, and the collective human imagination. The curiosity it sparked in 2007 has not faded. Rather, it has evolved, deepened by technological progress, enriched by theoretical advancement, and intensified by our unrelenting desire to know whether we are truly alone. One of the most compelling aspects of Gliese 581c lies in the interplay between its promise and its ambiguity. While its discovery was hailed as the opening of a new frontier in the search for habitable planets, it also underscored the limitations of our detection methods at the time. With no confirmed transit and limited data on its atmosphere or surface conditions, scientists have had to rely heavily on indirect measurements and computer simulations. These tools, while incredibly powerful, are inherently constrained by the assumptions they're built on. Every parameter fed into a simulation, planetary mass, orbital inclination, atmospheric composition, can significantly alter the predicted environment of Gliese 581c. For instance, the notion that Gliese 581c might be tidally locked presents one of the most significant challenges to its habitability. In a tidally locked state, one side of the planet would permanently face the red dwarf star Gliese 581, while the other side would remain in eternal darkness. This results in stark contrast between the day and night sides of the planet. Without a sufficiently thick and dynamic atmosphere, the heat from the sun-facing side might not redistribute efficiently, leading to searing temperatures on one hemisphere and freezing conditions on the other. However, if Gliese 581c possesses a dense atmosphere rich in greenhouse gases and capable of robust circulation, it could help moderate these extreme conditions, potentially creating a narrow Terminator zone, the twilight band between the light and dark hemispheres, where temperatures might be suitable for liquid water and, by extension, life. Such hypotheses have driven extensive modeling efforts, many of which have simulated everything from wind patterns to ocean currents, assuming oceans exist, to the planet's potential cloud cover. These simulations vary widely, but they share a common purpose: to refine our understanding of what makes a world habitable. It's an evolving concept, shaped as much by our knowledge of Earth as by the alien possibilities found elsewhere. Gliese 581c has been central to that evolution, serving as a kind of cosmic case study in astrobiological speculation. Then there is the question of atmosphere itself. What gases might shroud this mysterious world? Could Gliese 581c have retained its atmosphere in the face of potential stellar flaring? Does it possess a magnetic field strong enough to deflect stellar wind and cosmic radiation? The answers to these questions are critical, for without an atmosphere, any surface water would quickly evaporate or freeze, and the planet would be rendered barren. Earth's own magnetic field plays a vital role in protecting our biosphere, and a similar mechanism might be necessary for any habitable world orbiting a red dwarf. However, detecting magnetic fields of exoplanets remains beyond our current capabilities. We infer them based on planetary mass, rotation rate, and internal structure, all variables we must guess at for Gliese 581c. Still, there is hope that future missions will provide more definitive answers. Instruments like the James Webb Space Telescope, JWST, and the Extremely Large Telescope, ELT, may eventually help us glimpse signs of atmospheric composition around similar exoplanets, if not Gliese 581c directly. With advanced spectroscopy, astronomers could detect biosignature gases such as oxygen, ozone, or methane, compounds that, on Earth, are closely tied to biological activity. And that brings us to one of the most tantalizing aspects of this discussion: the possibility of life. What would life look like on a planet with a red sun in its sky? The spectral quality of light from Gliese 581 is different from our sun's. It is dimmer, redder, and more consistent in output. Photosynthesis, if it exists there, might have evolved differently. On Earth, plants appear green because they reflect green light and absorb red and blue. But under a red dwarf sun, alien photosynthetic organisms might have evolved to absorb the red and near-infrared light more efficiently, potentially giving them a different coloration, perhaps black, purple, or even silver. This isn't idle speculation. Scientists have conducted studies on how light conditions affect photosynthesis and have even engineered bacteria on Earth to thrive in infrared environments. If life has arisen on Gliese 581c, it could range from microbial mats to more complex, multicellular organisms. Though such speculation should be tempered with the understanding that we have no direct evidence of life or even habitability at this stage. Still, the allure of that possibility fuels our efforts. In this sense, Gliese 581c acts like a lighthouse in the night, distant, shrouded in mystery, yet beckoning us forward with the promise of discovery. This drive to explore further has also had societal and cultural ramifications. Gliese 581c, like other potentially habitable exoplanets, has inspired books, movies, academic conferences, and public fascination. It has been the subject of art, music, and even philosophical musings. What does it mean if there is another world out there, so similar and yet so alien? What ethical obligations would we have if we could one day reach it? Will we be explorers, ambassadors, or invaders? These questions stretch beyond astronomy into the realms of ethics, theology, and existential philosophy. The second Earth idea forces us to confront our identity as a species. Are we defined by our planet, or by our capacity to transcend it? If we discover life elsewhere, especially intelligent life, how will that redefine our place in the cosmos? Gliese 581c has prompted such questions not because it provides answers, but because it demands them. Even now, as we refine our models and build better telescopes, Gliese 581c remains a cornerstone of exoplanetary science. It helped establish the framework for defining potentially habitable planets. It demonstrated the importance of studying M-dwarf systems. It helped popularize the idea of the Goldilocks zone in mainstream media. And it set the stage for a whole new era of exploration. Today, the Gliese 581 system includes other planets as well, some disputed, some confirmed, with Gliese 581d and G once drawing similar attention for their potential habitability. But Gliese 581c stands apart because of its timing. It was one of the first to make us believe that another Earth might be within reach, not just metaphorically, but in the actual sense of scientific and technological progress. We are still far from visiting Gliese 581c. Located about 20.4 light-years away in the constellation Libra, it lies well beyond the reach of current spacecraft. Even traveling at the speed of the Voyager probes, which move at around 17 kilometers per second, it would take over 300,000 years to get there. Yet, projects like Breakthrough, Starshot, and Vision pushing tiny light-sail spacecraft to a significant fraction of the speed of light using powerful Earth-based lasers. At 20% of light speed, a probe could reach Gliese 581 in about a century. While such missions are still theoretical, they're increasingly within the realm of engineering feasibility. In the meantime, Gliese 581c continues to inspire, not because it is fully understood, but because it isn't. Its partial veil invites curiosity, critical thinking, and a re-examination of what life and habitability truly mean. As instruments improve, data accumulate, and theoretical models advance, we edge closer to a future in which exoplanets like Gliese 581c are not merely entries in a catalog, but destinations in a grand human journey. A journey not just across space, but toward deeper understanding. We move forward not because we know what we'll find, but because not knowing is the most powerful fuel we have. The mystery of Gliese 581c is more than just a scientific curiosity. It's a symbol of the frontier itself. In every great epoch of exploration, humanity has been driven by the unknown, compelled to venture beyond the horizon not because it was safe or simple, but because it was there. In that sense, Gliese 581c mirrors our past as much as it predicts our future. Just as the oceans once concealed undiscovered continents, the void of space now veils potentially Earth-like worlds that challenge our assumptions and spark our ambitions. While Gliese 581c ignited public fascination due to its early identification as a potentially habitable planet, its true legacy is found in how it reshaped our scientific methodologies and priorities. After its discovery, astronomers began to more rigorously define what habitable actually means. The simplistic notion of a habitable zone, merely being at the right distance from a star, gave way to more complex assessments that considered atmosphere, albedo, planetary composition, magnetic shielding, and even geological activity. Gliese 581c taught us that habitability is not a binary condition, but a spectrum, a delicate balance of interdependent variables that together create the possibility of life. The work done around Gliese 581c has also led to a more nuanced understanding of red dwarf systems in general. Red dwarfs make up nearly 75% of the stars in the Milky Way, yet they were long considered poor candidates for hosting life-bearing planets due to their volatile activity in narrow habitable zones. But the attention Gliese 581c attracted shifted the paradigm. It demonstrated that red dwarf systems are not just viable candidates. They may be the most abundant opportunity for discovering life outside our solar system. This realization opened the floodgates for surveys focusing specifically on these types of stars, leading to the discovery of additional intriguing planets, such as Proxima Centauri b, TRAPPIST 1e, and LHS 1140b. The specter of tidal locking, while often viewed as an obstacle to habitability, has even come under reconsideration. Atmospheric and oceanic models now show that tidal locking may not be the deal-breaker we once thought. The climate of a tidally locked planet can be stabilized by strong atmospheric circulation, allowing for temperate conditions in the Terminator zone or even across broader areas if the planet has a thick enough atmosphere. This reevaluation has not only improved the outlook for Gliese 581c, but for a vast number of similar exoplanets that were previously dismissed as uninhabitable. Another important area of research that Gliese 581c helped catalyze is the concept of planetary evolution. Planets, like stars, are dynamic. They evolve over billions of years, and their habitability can fluctuate dramatically during their lifespans. A world that is uninhabitable today may have been a cradle for life in the distant past, or could become one in the far future. Considering Gliese 581c's age, which is likely comparable or even older than Earth's estimated 4.5 billion years, it may have undergone dramatic transformations. If life ever emerged there, it may have had enough time to develop, adapt, or perish. This raises fascinating questions about extinct biospheres and the possibility of discovering fossilized evidence of life on other planets. Moreover, the question of extremophiles, organisms that thrive in harsh conditions on Earth, adds a layer of plausibility to the idea that life could exist on Gliese 581c, even under conditions that would be hostile by our standards. On Earth, extremophiles have been found in boiling hydrothermal vents, sub-zero Antarctic lakes, and even in high-radiation environments, such as the cooling pools of nuclear reactors. If Earth life can thrive in such extremes, then it's plausible that entirely different forms of life could exist in the alien conditions of Gliese 581c. Life may not require conditions exactly like Earth's. It may just need time, energy, and chemistry. We must also consider the possibility that life on Gliese 581c, if it exists, could be based on entirely different biological principles. Life, as we know it, is carbon-based and relies on water as a solvent. But what if life could emerge based on silicon, or utilize ammonia or methane in place of water? The existence of such life would stretch our definitions and force us to think beyond the narrow confines of terrestrial biology. Gliese 581c, in its mysterious inaccessibility, challenges us to expand not only our scientific models, but our imaginations. All this speculation serves a deeper purpose. It helps refine our search parameters. By analyzing what we know, or think we know, about Gliese 581c, we improve our ability to identify other exoplanets that might be even better candidates for life. Every bit of data, every model, every theory feeds into a vast and growing system of knowledge that brings us incrementally closer to discovering a second Earth. But let us not forget that Gliese 581c is also a lesson in humility. Some early studies claimed it was firmly in the habitable zone. Others later suggested it might be too hot. Some models showed possible stability. Others suggested wild climate fluctuations. Even the existence of certain planets in the Gliese 581 system was debated for years, with researchers clashing over data interpretation and signal noise. This back and forth reveals the inherently iterative nature of science. Understanding does not emerge in a straight line. It oscillates, challenges, corrects, and converges over time. Still, that debate is part of what makes Gliese 581c so enduringly fascinating. It doesn't sit comfortably in any scientific category. It resists easy classification and keeps evolving in our minds as new tools emerge and old data is reevaluated. It's not a solved mystery. It's an ongoing inquiry. Looking forward, the tools of tomorrow may finally allow us to characterize Gliese 581c with more precision. We may someday be able to image its atmosphere directly, detect weather patterns, or even identify surface features like continents or oceans. With next-generation telescopes and long-range space missions in development, such ambitions no longer belong solely to science fiction. Imagine a future where we receive direct spectroscopic signatures from Gliese 581c, revealing not just the presence of an atmosphere, but its precise components. Imagine finding oxygen, methane, and carbon dioxide in proportions that strongly suggest biological activity. That single piece of evidence, indirect though it may be, would change everything. It would imply that life is not unique to Earth. It would prove that biology is not an earthbound phenomenon, but a cosmic one. And if that day ever comes, we may look back and see Gliese 581c not just as one of many candidates, but as a pioneer, a symbol of a turning point in human understanding. Still, even if life is never found there, Gliese 581c will have served its purpose. It broadened the scope of our inquiry. It galvanized the field of exoplanetary science. It connected distant star systems to the minds and dreams of people here on Earth. And that alone makes it a world worth studying, worth imagining, and perhaps one day, worth visiting. In the deepest sense, Gliese 581c is not just a planet. It is a mirror reflecting our quest for meaning and belonging in a universe too vast to comprehend, yet too beautiful to ignore. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.